Welcome, we're so happy you tuned in tonight. Before we get started, I'd love to know, where are you watching from? Drop it in the comments. Now, let's get comfortable and drift into deep, peaceful sleep together. Saturn's rings are a wide, thin disk of countless small particles orbiting the planet, and when you picture them from far away, they look almost solid, like a great shining band wrapped around the pale yellow globe. But if you could drift closer, slowly enough to see the details emerge, you'd realize that what seemed like a single structure is actually more like a drifting swarm of icy pieces, each one following its own quiet path through space. Most of these ring particles are made largely of water ice, which is part of why the rings look so bright when sunlight touches them. Water ice is remarkably good at reflecting light, so even though the rings are made of separate fragments, they shine back at us with a steady, cool glow that makes them visible across the vast distance between Saturn and Earth. The particles themselves come in many sizes. Some are as small as grains of sand or tiny pebbles, barely larger than a speck of dust. Others are bigger, perhaps the size of a snowball, or even a boulder. A few might be as large as a small house, though these are rare. The important thing is that none of them are permanently stuck together into one solid object. Instead, they orbit Saturn individually, each one held in place by gravity, following a stable path like cars moving in gentle lanes around a roundabout. The rings themselves don't spin as one piece. They're more like a collection of travellers all going in the same general direction, but each at their own speed, depending on where they are. Saturn is not the only planet with rings. Jupiter has rings, and so do Uranus and Neptune, but Saturn's rings are by far the most bright and dramatic to see. They're the ones that catch your attention when you look at images of the outer solar system, the ones that make Saturn instantly recognisable. The rings are extremely wide compared to how thin they are. If you imagine the rings as a giant sheet of paper spread around a globe, you'd have a sense of their proportions. They stretch out for hundreds of thousands of kilometres across, but in many places they're only a few metres thick, sometimes just tens of metres, sometimes even less. That thinness is part of what makes them so delicate and beautiful. From certain angles, the rings can nearly disappear. This happens when we're looking at them edge-on, when the thin disk is oriented so that we're seeing it from the side rather than from above or below. At those times, the rings become almost invisible, like a line so fine it's hard to detect even with a good telescope. But when the angle changes again, when Saturn's orientation shifts in its orbit, and we can see the rings tilted toward us, they reappear in all their brightness, and the effect is almost magical, as if the planet had opened a quiet fan of light. The rings are not perfectly smooth. If you could look closely enough, you'd see that they have bands, gaps, and delicate textures. Some regions are bright and densely packed with particles, while others are darker and more translucent. There are divisions where the material thins out or nearly vanishes, and there are places where the particles seem to gather more thickly, like snow piling up in certain drifts. A calm way to picture the rings is as a quiet halo made of ice, turning slowly in sunlight, reflecting back a steady glow that speaks to the gentle order of orbital motion. Let's drift a little closer now, like we're floating above the ring plane, noticing how the ring system is organised into named sections. Saturn's main bright rings are commonly labelled the A, B and C rings, and these labels come from the order in which astronomers discovered and identified them, not necessarily from their position. The B ring is generally the brightest and most dense of the main rings. It's the one that stands out the most when you look at Saturn through a telescope, the region where the particles are packed closely enough that the ring looks almost solid. The B ring reflects a lot of sunlight, and it has a thickness to its appearance, a kind of visual weight that makes it the centerpiece of the whole ring system. The A ring is outside the B ring, farther from Saturn, and it contains many fine structures and narrow gaps. It's bright as well, though not quite as intensely packed as the B ring, and when you study it closely, you can see that it has layers of detail, small divisions, wavering edges, and regions where the brightness changes subtly. The A ring is like a carefully woven fabric with threads that vary in density and spacing, and it rewards close attention with its complexity. The C ring lies closer to Saturn than the B ring, and it's more translucent. If the B ring is like a thick curtain, the C ring is more like a veil, a region where the particles are spread out enough that you can see through them a little bit. The C ring doesn't catch as much light, and it has a softer, more subdued appearance. It blends quietly into the background, and you have to look carefully to see its edges and structure. Between the A ring and the B ring, there's a famous wide gap called the Cassini division. It's named after the astronomer Giovanni Domenico Cassini, who observed it in the 17th century. The Cassini division looks like a dark band separating the two bright rings, and for a long time people thought it might be completely empty, a true gap in the ring system. But despite its name, the Cassini division is not completely empty. There is still material in it, though the particles are much more sparse than in the bright rings on either side. It's a region where the density drops off sharply, creating a noticeable dark line when viewed from a distance, but up close, you'd still find ice and dust drifting through that space. There are also fainter rings closer in, including the D ring, which lies between the C ring and Saturn's cloud tops. The D ring is extremely faint and difficult to see, a ghostly presence that only becomes visible under certain conditions. Farther out, Saturn has a thin, narrow F ring that looks like a delicate strand, almost like a thread pulled tight around the outer edge of the main rings. The F ring is one of the most intriguing parts of the ring system because it doesn't behave the way you might expect a simple ring to behave. It has kinks and braids, regions where it looks twisted or clumped, and it changes over time in ways that suggest it's actively being shaped by forces we'll explore in a moment. Saturn also has broader, fainter rings like the E ring, which is linked to material from a moon. The E ring is much more spread out than the main rings, and it's made of very fine particles that scatter light in a different way. It forms a kind of soft halo far from Saturn, a region where the ring system becomes less a disk and more a diffuse cloud. The rings form a layered system, like shelves of softly separated brightness, each one distinct but part of the same gentle architecture. Now that the map feels familiar, we can explore what the rings are made of. Tiny pieces, each following simple rules. Many ring particles are mostly water ice, which makes the rings bright and reflective. Water ice is one of the most common materials in the outer solar system, and it's particularly good at bouncing sunlight back toward the observer. That's why the rings can look so brilliant, even though they're made of small fragments, rather than one solid surface. The ice in the rings can be relatively clean in many places, which helps sunlight bounce back toward us without being absorbed or scattered away. But the ice isn't always pure. Some particles contain dust or rocky material mixed in with the ice, and these impurities can change the way a particle reflects light, making some regions of the rings slightly darker or more reddish in colour. Ring particles can collide gently, like slow-moving snowballs in orbit, because the particles are travelling at similar speeds and mostly in the same direction. Their collisions tend to be soft rather than violent. When two particles bump into each other, they might bounce apart, or they might stick together for a little while before separating again. These collisions tend to keep the particles from clumping into one big object. If the particles were left entirely alone, gravity might slowly pull them together, but the constant gentle bumping breaks up any clumps that start to form and keeps the ring material distributed. Each particle follows an orbit, but small nudges from collisions can change a particle's path slightly. A collision might slow a particle down a little, or speed it up, or push it slightly inward or outward. These changes are small, but over time they add up, and they contribute to the way the rings spread out and maintain their structure. The rings behave like a granular disc, meaning a system of many small pieces moving together. It's a bit like sand flowing through a funnel, or grains of rice settling in a jar. Each individual piece follows its own path, but the overall behaviour of the system is smooth and predictable. The system can form ripples and waves, even though it's made of separate particles. This might seem surprising at first. How can a collection of independent pieces create patterns that look like waves? The answer has to do with the way gravity and motion interact. When a disturbance travels through the ring system, perhaps caused by a moon passing nearby, or by the gravitational pull of Saturn itself, the particles respond by shifting their positions slightly. Some particles move a little closer together, while others spread out, and the result is a ripple that travels through the ring like a wave moving across the surface of a pond. The rings can have different particle sizes in different regions, and this variation adds another layer of texture to the system. Some regions might be dominated by small grains, while others contain more large boulders, and the mix of sizes affects how the ring looks and how it behaves. In a soothing way, the rings show how complexity can emerge from simple pieces repeating simple motion. Each particle is just orbiting Saturn, following the basic rules of gravity and motion, but when you put billions of particles together, All orbiting at slightly different speeds and distances, you get a system that's rich in detail and beauty. The rings don't need a central plan or a guiding hand to create their structure. They just need the steady pull of gravity and the patient repetition of orbital motion, and the patterns emerge naturally, like frost forming on a window or sand settling into ripples on a beach. With the particles in mind, let's let gravity do its quiet work and see why the rings stay spread out instead of forming a single moon. Ring particles orbit Saturn at different speeds depending on their distance from the planet. Particles close to Saturn orbit faster than particles farther away. This is a fundamental rule of orbital mechanics, related to the way gravity gets stronger as you get closer to a massive object. If you're orbiting close to Saturn, you feel a stronger pull, and you have to move faster to maintain your orbit. If you're farther out, the pull is weaker, and you can move more slowly and still stay in a stable path. This difference in speed is called differential rotation, and it helps stretch structures into long bands. Imagine you have a row of particles lined up side by side, all at slightly different distances from Saturn. The inner particle is moving faster, the outer particle is moving slower, and the middle particle is somewhere in between. As time goes by, the faster particle pulls ahead, and the slower particle falls behind, and the row stretches out into a long, thin line. This is what happens to the rings. Any clump or cluster of particles gets stretched by differential rotation, and over time the clumps turn into streamers and bands. It's a gentle process, but it's relentless, and it's one of the reasons the rings look the way they do. Saturn's gravity pulls particles inward, while their orbital motion keeps them from falling straight down. This is the essence of an orbit. If you drop a particle straight towards Saturn with no sideways motion, it would fall directly down and eventually crash into the planet. But if you give the particle some sideways motion, some velocity perpendicular to the direction of Saturn's gravity, then the particle will curve around the planet instead of falling straight in. The pull of gravity keeps bending the particle's path, and the particle keeps moving sideways, and the result is an orbit. The balance between gravity and sideways motion is what makes an orbit stable. The particle is constantly falling towards Saturn, but it's also constantly missing Saturn because of its sideways speed, and the two motions balance out into a circular or elliptical path. Inside a certain region, tidal forces can make it hard for large objects to form and stay intact. This region is related to the idea of the Roche limit, which is a concept that helps explain why Saturn has rings in the first place. The Roche limit is the distance from a planet inside which the planet's gravity is strong enough to pull apart a large object that's held together only by its own gravity. Imagine a small moon made of rubble and ice, orbiting Saturn. If the moon is far enough away, it can hold itself together just fine. But if it drifts too close to Saturn, the side of the moon facing the planet feels a stronger pull than the side facing away, and this difference in pull, the tidal force, starts to stretch the moon. If the tidal force is strong enough, it can overcome the moon's own gravity and pull the moon apart into pieces. Those pieces then continue to orbit Saturn, and they become part of the ring system. Collisions between particles also break up larger clumps and keep the ring material distributed. Even if a few particles do stick together and start to form a small moonlet, the moonlet is likely to get hit by another particle sooner or later, and the collision can break it apart again. The result is a broad, thin disk rather than a single solid ring. The particles are spread out over a huge area, and they're all moving in nearly the same plane, which keeps the disk thin. The rings can feel like a calm demonstration of balance, pull and motion held in steady harmony. Gravity pulls inward, motion carries sideways, and the two forces work together to create a stable, lasting structure that can persist for millions of years. Now we can glide over the ring surface and notice the beautiful patterns, gaps, divisions, and narrow lanes etched by gentle forces. The Cassini division, which we mentioned earlier, is shaped in part by gravitational resonances with Saturn's moons. A resonance happens when orbital periods form a simple ratio, creating repeating nudges. For example, imagine a ring particle that orbits Saturn exactly twice for every one orbit of a nearby moon. Every time the moon completes one orbit, the ring particle is in the same position relative to the moon, and the moon's gravity gives the particle a little tug. This tug happens over and over again, always in the same place in the particle's orbit, and the repeated nudges add up over time. Eventually the particle's orbit gets changed, it might get pushed inward or outward, or its orbit might become more elliptical, and the result is that the particle is no longer in that region. Over millions of years, these resonances can clear out entire sections of the ring, creating gaps and divisions. These repeating nudges can clear out some regions and sharpen boundaries. The edges of the Cassini division, for instance, are quite sharp when you look at them closely. The division isn't just a gradual thinning of particles, it's a relatively abrupt drop in density, and that sharpness comes from the way resonances sweep particles out of certain zones. The A-ring contains the Encke gap, a narrow gap with a moon inside it. The small moon Pan orbits within the Encke gap and helps maintain its structure. Pan is only about 28 kilometers across, but it's large enough to have a noticeable gravitational effect on the ring particles around it. As Pan orbits, it sweeps up particles in its path and pushes others out of the way, and the result is a clear gap where the moon travels. The Keeler gap is another narrow gap near the outer edge of the A-ring. The moon Daphnis orbits in the Keeler gap and can create wavy edges along the gap. Daphnis is even smaller than Pan, only about 8 kilometers across, but it's enough to disturb the particles at the edges of the gap. When Daphnis passes by, its gravity pulls on the nearby particles, and the edges of the gap develop little waves, like ripples in water. These waves are visible in high-resolution images, and they show how even a very small moon can have a noticeable effect on the ring structure. Spiral density waves appear in rings as tightly wound ripples caused by resonances. These waves are one of the most beautiful and intricate features of Saturn's rings. They look like closely spaced lines or bands that spiral outward from a central point, and they form when a resonance causes particles to bunch up in certain regions and spread out in others. The waves are a bit like the grooves on a vinyl record, or like the ripples you see when you drop a stone into a still pond. They're a visual record of the gravitational interaction between the rings and the moons, a kind of pattern that the rings remember and display. Bending waves can also occur, where ring material is tilted slightly up and down like a slow, soft swell. Instead of changing the density of particles in the ring plane, bending waves change the vertical position of the particles, so parts of the ring rise a little above the main plane and other parts dip a little below. These waves can be caused by resonances or by interactions with moons that have inclined orbits. They add another layer of structure to the rings, and they show how the ring system can respond to forces in 3 dimensions, not just in the flat plane of the disk. These patterns are like the rings recording gentle gravitational music in visible lines. Every gap, every wave, every division is a trace of the way gravity has shaped the system over time. The rings don't just sit there unchanged. They respond to the moons and to Saturn itself, and they create patterns that reflect those interactions. It's a kind of slow, patient artistry, where the medium is ice and dust and the tools are gravity and motion, and the result is a structure of astonishing beauty and complexity. From those etched patterns, we can float outward to the thinnest, most delicate strand, the F-ring and its quiet guardians. The F-ring is a narrow ring just outside the main bright rings, and it's one of the most dynamic and changeable parts of the ring system. It often looks braided or kinked, like a thread that has been lightly twisted. Sometimes the F-ring appears as a single strand, and sometimes it looks like multiple strands woven together. The structure changes over time, and images taken years apart can show significant differences in the way the ring looks. The F-ring is shaped by nearby moons called shepherd moons. 2 famous shepherd moons are Prometheus and Pandora, and they orbit on either side of the F-ring. Their gravity helps confine the ring and sculpt its edges. Prometheus orbits just inside the F-ring, and Pandora orbits just outside it, and together they act like shepherds guiding a flock. Their gravitational pulls keep the ring particles from drifting too far inward or outward, and they maintain the narrow structure of the ring. Prometheus can create streamers and clumps by pulling on ring material during close passes. Because Prometheus's orbit is slightly elliptical, it doesn't always stay at the same distance from the F-ring. Sometimes it gets closer, and when it does, its gravity pulls more strongly on the ring particles, creating disturbances that show up as streamers or channels in the ring. These disturbances are temporary, they fade and change as the particles continue to orbit, but they're visible in high-resolution images, and they show how active the F-ring is. The F-ring can contain small, temporary clumps that form and disperse over time. Some of these clumps may be short-lived moonlets that start to gather and then break apart. A moonlet might form when a few particles stick together, but if it's in a region where collisions are common, it won't last long. The constant jostling and nudging from other particles combined with the gravitational effects of Prometheus and Pandora means that the F-ring is always changing, always reshaping itself. The F-ring shows how a very thin structure can still be lively and detailed. Even though it's only a few kilometers wide, much narrower than the main rings, it has more variation and complexity than you might expect. It's a gentle reminder that even the finest lines in nature can be held steady by quiet, repeated pulls. The shepherd moons don't have to be large or dramatic to have an effect. They just have to be there, orbiting patiently, tugging on the ring particles over and over again, and the structure emerges from that steady interaction. Now we'll drift farther into the faint outer rings, where the glow becomes softer and the ring material becomes more spread out and airy. The E-ring is much broader and fainter than the main rings. It extends over a huge distance, from well inside the orbit of the Moon, Mimas all the way out past the orbit of Dione. The E-ring is made largely of very tiny icy particles, more like mist than pebbles. These particles are so small that they scatter light in a different way than the larger particles in the main rings. Instead of reflecting light back in a bright concentrated beam, the tiny particles scatter light in all directions, creating a soft, diffuse glow. The E-ring is strongly linked to Saturn's moon Enceladus, which is one of the most fascinating moons in the entire solar system. Enceladus has geyser-like plumes that release water ice into space. These plumes shoot out from cracks in the moon's icy surface, and they send tiny ice crystals flying outward at high speed. Some of that released ice becomes part of the E-ring. The plumes are powered by heat from inside Enceladus, possibly from tidal heating caused by the gravitational pull of Saturn and other moons. The fact that Enceladus is geologically active with liquid water beneath its icy crust makes it one of the most exciting places to study in the search for conditions that might support life. Because the particles in the E-ring are small, sunlight can scatter through them in a gentle haze. The E-ring doesn't have the sharp boundaries or the bright defined appearance of the main rings. Instead, it's more like a cloud, a region where the density of particles gradually increases and then gradually decreases again. If the main rings are like shining shelves, these fainter rings are like a thin fog of ice drifting quietly outward. Saturn also has a faint G-ring, which contains an arc of brighter material. The G-ring lies between the orbits of Mimas and Enceladus, and it's made of very fine dust. The arc is a region where the dust is slightly more concentrated, and it shows up as a brighter patch in images. The G-ring is thought to be maintained by small moonlets, or by dust kicked up from larger objects by micrometeorite impacts. It's another example of how the ring system has layers of structure at different scales, from the bright main rings down to these faint, dusty halos. Some faint rings can be influenced by dust and small particles interacting with Saturn's magnetic environment. Saturn, like Earth, has a magnetic field, and charged particles can become trapped in this field and move along the field lines. Dust grains can pick up electric charges from sunlight or from interactions with other charged particles, and once charged, they can be affected by the magnetic field. This interaction can help maintain some of the faint rings, or it can cause particles to spiral inward or outward over time. The ring system includes both bright bands and soft clouds of material, and each region has its own story of how it formed and how it's maintained. With those soft outer structures in view, we can talk about where the rings might have come from, several calm possibilities still being studied. Scientists are still studying the exact origin of Saturn's rings, and there isn't one single answer that everyone agrees on. Instead, there are several possibilities, each supported by different lines of evidence, and the truth might involve a combination of these ideas. One possibility is that the rings formed from a moon or icy body that broke apart. If a small moon wandered too close to Saturn, tidal forces could have pulled it apart, and the fragments could have spread out into a ring. Alternatively, a moon might have been shattered by a collision with a comet or asteroid, and the debris could have formed the ring system. Another possibility is that ring material formed early in Saturn's history and evolved over time. According to this idea, the rings might have been present since shortly after Saturn itself formed, or they might have formed from material left over from the planet's formation. Over billions of years, the rings would have changed as particles collided, as material was added by impacts from comets, and as some material was lost to Saturn's atmosphere or to moons sweeping through the rings. Impacts from comets or small bodies could contribute material or reshape existing rings. The outer solar system is full of small icy objects, comets, asteroids, and chunks of debris, and these objects occasionally collide with Saturn's moons or with the rings themselves. Each collision can add new material to the ring system, or it can break up existing particles into smaller pieces. Over long timescales, these impacts can have a significant effect on the composition and structure of the rings. If a moon came too close to Saturn, tidal forces could have helped pull it apart. This is the Roche limit scenario we mentioned earlier, and it's one of the leading ideas for how the rings might have formed. The key point is that the moon doesn't have to be very large. Even a relatively small moon, if it's made of loosely bound material, can be torn apart by tidal forces if it gets close enough to Saturn. Once the moon breaks up, the pieces continue to orbit, and they gradually spread out into a disk. Collisions among ring particles can grind material down into smaller pieces over long periods. This process is called collisional erosion, and it's one of the reasons the rings are made of such a variety of particle sizes. When two particles collide, they can chip pieces off each other, and those chips become smaller particles. Over millions or billions of years, this grinding can turn large boulders into pebbles, and pebbles into dust. The process also tends to smooth out the surfaces of the particles, which might contribute to the brightness of the rings. The brightness of the rings suggests a large amount of relatively clean ice in many regions. This is one of the clues that scientists use to think about the age of the rings. If the rings were very old, billions of years old, you might expect them to have accumulated more dust and darkened over time. The fact that they're so bright suggests that either the rings are relatively young, or there's some process that keeps them clean, such as particles sticking together and then being removed by sweeps from moons or by falling into Saturn. Some research discusses whether the rings are young or old, and the debate continues as measurements improve. Recent data from the Cassini mission, which ended in 2017, suggested that the rings might be younger than previously thought, perhaps only a few 100 million years old rather than billions of years old. This estimate comes from measuring the rate at which material is falling from the rings into Saturn's atmosphere, and from studying the mass of the rings. But the question is still open, and different methods give different answers, so scientists continue to refine their models and gather more data. Even without a final answer, the ring system is clearly dynamic, changing slowly like a long, quiet weather pattern. The rings are not frozen in time, they're evolving, responding to the forces acting on them, and they'll continue to change in the future. It can be soothing to let the origin remain a gentle mystery for now, like a story with multiple calm chapters. The rings are there, they're beautiful, and they're telling us something about the history of Saturn and the solar system, even if we haven't decoded every detail yet. Now we'll visit the explorers that helped us see the rings clearly, spacecraft and telescopes that turned distant light into detailed understanding. Early astronomers noticed Saturn's strange shape before understanding it had rings. When Galileo Galilei first observed Saturn through his small telescope in the early 17th century, he saw something odd on either side of the planet, but his telescope wasn't powerful enough to show what it was. He described Saturn as having ears, or handles, and he didn't know what to make of the observation. A few years later, the rings appeared to vanish. This was when Saturn's rings were oriented edge-on as seen from Earth, and Galileo was confused about what had happened. Better telescopes eventually revealed the rings more clearly as separate from the planet. In the mid-17th century, the Dutch astronomer Christian Huygens used an improved telescope to observe Saturn, and he was the first to correctly describe the rings as a flat disk surrounding the planet. Later, Cassini observed the gap that now bears his name, and other astronomers continued to study the rings, mapping their structure and measuring their properties with ever-improving instruments. The spacecraft Voyager 1 and Voyager 2 provided major close-up images and measurements. These two spacecraft flew past Saturn in 1980 and 1981, and they sent back images that showed the rings in unprecedented detail. The Voyager images revealed that the rings were much more complex than anyone had thought. What had looked like a few broad bands from Earth turned out to be made up of thousands of narrow ringlets, and the images showed gaps, waves, and fine structures that had never been seen before. The Voyager missions also measured the temperature of the rings, the composition of the particles, and the way the rings interacted with Saturn's magnetic field. The mission Cassini spent many years studying Saturn and its rings in detail. Cassini was launched in 1997, arrived at Saturn in 2004 and orbited the planet for 13 years before its mission ended in 2017. During that time, Cassini made hundreds of orbits, observing the rings from every angle and at every distance. Cassini observed ring structure, waves, and fine gaps with remarkable clarity. The spacecraft used multiple instruments to study the rings, cameras to take visible light images, spectrometers to measure the composition of the particles, and radio instruments to probe the rings' density and structure. Scientists study rings by measuring how they reflect sunlight at different wavelengths. Different materials reflect light in different ways, and by breaking the light into a spectrum, like a rainbow, scientists can identify the substances present in the ring particles. For example, water ice has a distinctive signature in the infrared part of the spectrum, and by measuring the strength of this signature, scientists can estimate how much ice is in the rings and how pure it is. They also study rings using radio signals sent through the rings to see how the signal changes. This technique is called radio occultation, and it works a bit like shining a flashlight through a fog. When Cassini passed behind the rings as seen from Earth, it sent a radio signal back to Earth, and that signal had to travel through the rings to reach us. By measuring how the signal was weakened or scattered by the ring particles, scientists could calculate the density of particles in different regions and learn about the size distribution of the particles. When a star passes behind the rings, the way its light dims can reveal ring density and structure. This technique is called stellar occultation, and it's similar to radio occultation but uses starlight instead of radio waves. As a star moves behind the ring particles block some of the starlight, and the amount of dimming tells you how dense the particles are in that part of the ring. By watching many stars pass behind different parts of the rings, scientists can build up a detailed map of the ring structure. These methods are like gentle shadow readings, turning faint changes into information. They don't require physically touching the rings or disturbing them in any way. Instead, they use light and radio waves, things that pass through the rings naturally, and they extract information from the subtle ways those signals are changed. The more we observe, the more the rings feel like a living system, quietly patterned and carefully measurable. Every new observation adds another piece to the puzzle, and the picture becomes clearer and richer. Let's pause for a moment and think about what it means for the rings to be so thin. When we say the rings are thin, we're talking about a dimension that's almost impossible to comprehend at first. The rings stretch out, across a distance of more than 280,000 kilometers from their inner edge to their outer edge. But in many places they're only 10 to 30 meters thick. That's like comparing the width of a football field to the thickness of a sheet of aluminum foil. It's a ratio that's hard to hold in your mind, but it's important because it tells us something fundamental about how the rings behave. The thinness comes from the way the particles move. They're not moving randomly in all directions. They're mostly moving in the same plane, like cars on a very wide highway. When particles collide, they can bounce up or down a little bit, but those vertical motions tend to average out over time. If a particle gets knocked upward, it will eventually fall back down due to Saturn's gravity, and if it gets knocked downward, it will bounce back up. The net result is that the particles settle into a flat disk, and the disk stays flat because the particles keep bumping into each other and evening out their vertical motions. This process is a bit like what happens when you shake a box of cereal. If you shake it gently, the pieces inside settle into a more compact arrangement, and the box becomes flatter as the empty space gets squeezed out. The ring particles are doing something similar, except instead of being shaken by hand, they're being jostled by collisions, and instead of settling into a box, they're settling into a thin disk around Saturn. It's a slow, patient process, but it's very effective, and it's why the rings have such a dramatic aspect ratio. The thinness also affects the way we see the rings. When the rings are tilted toward us, we see them as wide, bright bands, and we can see all the structure and detail in the ring system. But when the rings are edge-on, they become almost invisible, and Saturn looks like a plain sphere with no rings at all. This happens roughly every 15 years, because Saturn takes about 29.5 years to orbit the Sun, and during that time the rings go through two periods when they're edge-on as seen from Earth. These edge-on periods are actually useful for scientists, because they make it easier to see faint moons and structures that would normally be hidden by the brightness of the rings. Now let's think more carefully about the particles themselves and what they're like up close. If you could somehow visit the rings and float among the particles, you'd find yourself in a strange and beautiful environment. The particles would be all around you, drifting past in their orbits, each one moving at a slightly different speed. Some would be tumbling slowly, reflecting sunlight as they turned, and others would be moving smoothly along their paths. The space between particles would be mostly empty. The rings look solid from a distance, but up close there's a lot of empty space. The particles would vary in size, shape, and brightness. Some would be almost perfectly spherical, smoothed by countless, gentle collisions over millions of years. Others would be irregular and jagged, perhaps freshly broken from a larger object. Some particles would be bright white, made of clean water ice that reflects sunlight efficiently. Others would be darker, with dust or rocky material mixed in, and they might have a greyish or brownish tint. The variety would be endless, and no two particles would be exactly alike. If you reached out and touched one of the particles, you'd find that it's cold, extremely cold. The temperature in the rings is far below freezing, typically around -180 degrees Celsius or even colder. At that temperature, water ice is as hard as rock, and the particles would feel solid and firm. The surface might be smooth in some places and rough in others, depending on the particle's history. Some particles might have small craters from impacts with tiny grains of dust, while others might be covered in a fine layer of frost. The particles would also be moving at different speeds depending on where they are in the ring system. In the inner parts of the rings, close to Saturn, the particles orbit faster, completing a trip around the planet in just a few hours. In the outer parts of the rings, the particles move more slowly, taking longer to complete each orbit. If you were floating in the middle of the A-ring, for example, the particles around you would be moving at about 20 kilometers per second, fast enough to cross a city in the blink of an eye. But because all the particles are moving in the same direction at similar speeds, the relative motion between neighbouring particles is much slower, just a few centimeters per second in many cases. It's this slow relative motion that makes the collisions gentle rather than destructive. The lighting in the rings would be remarkable. Sunlight would stream in from one direction, illuminating the particles and making them glow. But the light wouldn't be harsh or direct. It would be softened by the scattering from countless particles, creating a kind of diffuse glow that fills the space. Some particles would be in shadow, blocked from direct sunlight by other particles, and they would appear darker and more subdued. The contrast between the bright sunlit particles and the shadowed ones would create a sense of depth and dimension, and you'd be able to see the three-dimensional structure of the ring system in a way that's not possible from a distance. You might also see some particles that are backlit by sunlight, with light streaming through gaps and creating halos and glows. This kind of lighting can reveal very fine dust that's invisible under normal conditions, and it can make the rings look even more ethereal and delicate. The Cassini spacecraft captured images of the rings in this backlit geometry, and the results were stunning. The rings looked like gossamer threads and veils, with light shining through them and revealing structures that had never been seen before. Now let's consider the forces that shape the rings on larger scales. We've talked about gravity and collisions, but there are other factors at play as well. One of these is radiation pressure from sunlight. When sunlight hits a particle, it exerts a tiny push on the particle, just like the wind pushing on a sail. For large particles, this push is negligible, but for very small particles, grains of dust just a few micrometers across, the radiation pressure can be significant. It can push these tiny particles outward, away from the sun, and over time it can cause them to drift out of the ring system entirely. This effect helps explain why the rings don't have more dust than they do. If the rings were constantly grinding down particles into smaller and smaller pieces, you might expect the rings to become filled with dust over time, but the radiation pressure acts like a filter, removing the tiniest particles and leaving behind the larger ones. This helps keep the rings relatively clean, and prevents them from becoming a thick, dusty haze. Another force that affects the rings is the solar wind, which is a stream of charged particles flowing out from the sun. The solar wind interacts with Saturn's magnetic field, creating a complex environment around the planet. Some ring particles can become electrically charged by sunlight or by interactions with the solar wind, and once charged, they can be affected by Saturn's magnetic field. This interaction is most important for the faint dusty rings, where the particles are small enough to be easily influenced by electromagnetic forces. Saturn's magnetic field itself is an important part of the environment around the rings. The field is generated deep inside Saturn, where electrically conducting materials flow and create electric currents. These currents produce a magnetic field that extends far out into space, surrounding the planet and its rings. The field isn't perfectly symmetrical. It has a complex structure with regions where the field is stronger or weaker, and it changes over time in response to conditions inside Saturn and in the surrounding space. Charged particles from the solar wind and from Saturn's moons can become trapped in the magnetic field, spiraling along the field lines and bouncing back and forth between the planet's poles. These trapped particles form radiation belts, similar to Earth's Van Allen belts, and they create a hazardous environment for spacecraft. The Cassini mission had to navigate through these radiation belts carefully, and the spacecraft was designed to withstand high levels of radiation during its close approaches to Saturn. The interaction between the rings and the magnetic field is subtle but important. In some regions, the rings can actually absorb charged particles from the radiation belts, creating gaps or depressions in the particle population. These gaps can be detected by instruments that measure the intensity of radiation, and they provide a way to map the structure of the rings from the pattern of particle absorption. It's another example of how the rings affect their environment, not just through gravity but through electromagnetic interactions as well. Now let's think about how the rings change over time. We tend to think of the rings as permanent features, something that's always been there and always will be, but the reality is more complex. The rings are dynamic, evolving structures, and they're changing on timescales ranging from hours to billions of years. On short timescales, the rings respond to the gravitational tugs of passing moons, creating waves and disturbances that ripple through the system. These changes happen relatively quickly, and they can be observed by spacecraft over the course of days or weeks. On longer timescales, the rings evolve as particles collide and grind each other down, as material is added by impacts from comets and meteoroids, and as some material is lost to Saturn's atmosphere or to escaping moons. The Cassini mission provided some of the best evidence for how fast these processes are happening. One of Cassini's most important discoveries was the detection of material falling from the rings into Saturn's atmosphere. This material, which is mostly water ice mixed with some organic compounds and silicates, rains down on Saturn at a rate of thousands of kilograms per second. That might not sound like much compared to the total mass of the rings, but over time it adds up. If you extrapolate this loss rate backward in time, you can estimate how long the rings could have been losing material at this rate before they would have been depleted. The answer is surprising, only a few 100 million years, which is much shorter than the age of Saturn itself. This suggests that either the rings are relatively young, perhaps formed a few 100 million years ago from the breakup of a moon or a large comet, or there's some process that's replenishing the ring material and keeping the rings from disappearing entirely. The idea that the rings might be young is controversial, and it's still being debated by scientists. If the rings are young, it raises the question of why they formed when they did. Was there a specific event that triggered their formation, or is it just a coincidence that we happen to be living at a time when Saturn has rings? On the other hand, if the rings are old, then there must be some mechanism that's keeping them from fading away, and scientists are working to understand what that mechanism might be. One possibility is that the rings are being replenished by material from Saturn's moons. When a small meteoroid hits one of the moons, it can kick up a cloud of ice and dust, and some of that material can escape from the moon and become part of the ring system. This process is particularly effective for moons with weak gravity, where it doesn't take much energy to launch material into space. Over time, this steady trickle of material could balance out, the loss from the rings falling into Saturn, keeping the total mass of the rings roughly constant. Another possibility is that the rings are recycling material internally. Maybe particles that fall towards Saturn don't all make it all the way into the atmosphere. Maybe some of them get scattered by interactions with the magnetic field or with other particles, and they end up back in the rings. Or maybe there are processes that concentrate material in certain regions of the rings, creating temporary reservoirs that can later be redistributed. These are active areas of research, and scientists are using the data from Cassini to test different models and figure out which scenarios are most consistent with the observations. The age question is intimately tied to the composition of the rings. If the rings are mostly clean water ice, as the observations suggest, then how did they stay so clean over billions of years? One idea is that the rings have a kind of self-cleaning mechanism. When particles collide, they can break off small chips and fragments, and these fragments might carry away impurities, leaving behind cleaner ice. Or maybe the impurities tend to concentrate in certain particles, which then fall into Saturn more quickly, again leaving behind cleaner ice in the rings. It's also possible that there's ongoing bombardment by small icy comets that add fresh water ice to the rings and help maintain their brightness. The colour of the rings provides another clue about their composition and history. While the rings are mostly bright and white, they do have some variation in colour. Some regions are slightly more reddish, which might indicate the presence of organic compounds or iron-bearing minerals. These redder regions could be areas where impurities are more concentrated, or they could be places where the ice has been exposed to more radiation and has undergone chemical changes. By mapping the colour variations across the rings, scientists can learn about the distribution of different materials and about the processes that affect the ring particles. Now let's turn our attention to the way the rings interact with Saturn's atmosphere. The material falling from the rings doesn't just vanish when it reaches the planet. It has to go somewhere, and that somewhere is the upper atmosphere of Saturn. When the ring particles enter the atmosphere, they heat up due to friction with the atmospheric gases, and they vaporize, releasing water vapor, silicates, and organic compounds into the air. This material then mixes with the existing atmosphere and can affect its chemistry and structure. One of the effects of this ring rain is to change the composition of Saturn's upper atmosphere in certain regions. The material tends to fall near the planet's equator, because that's where the rings are, and it creates a kind of equatorial band where the atmosphere has more water and other ring-derived materials than it would otherwise. This can affect the temperature and density of the atmosphere in those regions, and it might even influence the formation of clouds and hazes. The ring rain also has implications for understanding Saturn's interior and evolution. The fact that material is constantly falling into the planet means that Saturn is gradually accreting mass from its rings, albeit at a very slow rate. Over the age of the solar system, this could add up to a significant amount of material, and it could affect the planet's overall composition and structure. It's another reminder that the rings and the planet are not separate systems. They're intimately connected, constantly exchanging material and energy. Another fascinating aspect of the rings is the way they create their own environment through electromagnetic effects. We mentioned earlier that charged particles can interact with Saturn's magnetic field, but there's more to the story. The rings themselves can become electrically charged through a process called photoelectric emission. When sunlight hits the surface of a ring particle, it can knock electrons out of the surface, leaving the particle with a positive charge. These free electrons then move through space, creating a population of charged particles around the rings. This charging process can have several effects. For one thing, it can cause particles to repel each other electrostatically, which might affect the spacing and arrangement of particles in the rings. It can also create electric fields that accelerate charged particles, sending them spiraling along magnetic field lines. And it can lead to the formation of plasma clouds and sheaths around the rings, where the density of charged particles is higher than in the surrounding space. The Cassini spacecraft carried instruments that could detect these charged particles and measure the electric and magnetic fields around the rings. The data revealed a complex and dynamic environment, with waves and disturbances propagating through the plasma, with electric currents flowing along the magnetic field lines, and with particles being accelerated and decelerated in response to changing conditions. It's a reminder that the rings are not just passive collections of ice and rock, they're active participants in the electromagnetic environment of the Saturn system. Let's shift now to thinking about the rings in the context of the broader solar system. Saturn's rings are unique in their size and brightness, but the basic physics that governs them applies to other ring systems as well. Jupiter, Uranus and Neptune all have rings, and while these rings are much fainter and less extensive than Saturn's, they're governed by the same principles of gravity, orbital mechanics, and particle interactions. Jupiter's rings, for example, are made mostly of very fine dust, probably kicked up from the planet's small inner moons by micrometeorite impacts. The rings are faint and difficult to see, but they were discovered by the Voyager spacecraft in 1979, and they've been studied in more detail by subsequent missions. The rings have several components, including a thin main ring and a broader, fainter halo ring that extends inward toward the planet. The structure of Jupiter's rings is shaped by the same kinds of resonances and gravitational interactions that affect Saturn's rings, but the outcome is different because the source material and the environment are different. Uranus has a system of narrow rings that are quite different from Saturn's broad, bright rings. Uranus's rings are dark, much darker than Saturn's, and they're composed of particles that are larger on average, more like gravel than like dust. The rings are confined to narrow bands, separated by wide gaps, and they're maintained by the gravitational influence of small shepherd moons. The ring system was discovered in 1977 when Uranus passed in front of a star and observers noticed that the star's light dimmed several times before and after the planet blocked, it indicating the presence of rings. Neptune's rings are similar to Uranus's in some ways, but they have one unique feature. They contain arcs, or regions where the ring material is clumped together instead of being spread evenly around the planet. These arcs are thought to be maintained by resonances with Neptune's moon Galatea, which nudges the particles and keeps them from spreading out. The arcs are a beautiful example of how subtle gravitational effects can create structure in ring systems, and they show that there's still a lot we don't understand about how rings behave. Beyond the giant planets, there are even ring systems around smaller bodies in the solar system. The asteroid Chariklo, for instance, was discovered to have 2 narrow rings when it passed in front of a star in 2013. This was a complete surprise because no one expected an object as small as Chariklo, it's only about 250 kilometers across, to have rings. The discovery showed that rings might be more common than we thought, and that they can form around bodies of very different sizes and types. All of these ring systems teach us something about the processes that shape planetary environments. They show us how particles interact under gravity, how moons can sculpt and maintain structures, and how impacts and collisions can create and destroy material. They also give us a window into the early solar system, when planets were still forming and the space around them was filled with debris and leftover material. Studying rings today helps us understand what conditions were like billions of years ago, and how the solar system evolved into the configuration we see today. Let's return to Saturn and think about what the rings look like at different times and from different perspectives. The appearance of the rings changes dramatically depending on the angle from which they're viewed and the lighting conditions. When the sun is behind the observer, the rings are brightly lit and show their full glory, with all the structure and detail visible. This is called the lit face of the rings, and it's the view we're most familiar with from images taken by spacecraft and telescopes. But when the sun is on the opposite side of the rings from the observer, the rings are backlit, and they look completely different. In this geometry, the light has to pass through the rings to reach the observer, and the amount of light that gets through depends on how transparent the rings are. The densest parts of the rings block most of the light, appearing dark, while the more transparent regions let more light through, appearing brighter. This backlit view can reveal structures that are invisible in normal lighting, such as very fine dust and tenuous ringlets. The Cassini spacecraft took advantage of this by observing the rings in both lit and backlit geometries, and by comparing the two views, scientists were able to learn a lot about the distribution of particle sizes and the density of the rings. The backlit images were particularly useful for studying the faint rings, like the E ring and the G ring, because these rings are much more visible when backlit than when lit from the front. The rings also change in appearance as Saturn moves through its orbit around the Sun. Because Saturn's rotational axis is tilted relative to its orbital plane, the angle at which sunlight hits the rings changes over the course of Saturn's year. At some times the Sun is high above the rings, shining down on the northern face, and at other times the Sun is below the rings, shining up on the southern face. And twice during each orbit the Sun passes through the plane of the rings, creating a period called Saturn's equinox. During equinox, the Sun shines edge onto the rings, illuminating them in a very thin band and casting long shadows from any particles or structures that stick up above the ring plane. This is an ideal time to look for small moons and moonlets embedded in the rings because their shadows can be much larger and more visible than the moons themselves. Cassini observed Saturn's equinox in 2009, and the images revealed several previously unknown moonlets and showed features in the rings that had never been seen before. The changing seasons on Saturn also affect the rings in more subtle ways. The temperature of the ring particles varies depending on how much sunlight they receive, and this can affect the physical properties of the ice. When the particles are warmer, the ice can be slightly softer and more prone to sticking together during collisions. When the particles are colder, the ice is harder and more brittle. These differences are small, but over long timescales they might affect the evolution and structure of the rings. Now let's think about what it would be like to observe the rings from the surface of Saturn if Saturn had a solid surface to stand on. Of course, Saturn is a gas giant with no solid surface in the way we usually think of it, but we can imagine what the view would be like from deep in the atmosphere, looking up at the rings overhead. From the equator of Saturn, the rings would appear as a thin, bright line stretching across the sky from horizon to horizon, directly overhead. The line would be incredibly narrow, because you'd be looking at the rings edge-on, and they'd appear as a luminous thread dividing the sky in half. As you moved away from the equator, toward higher latitudes, the rings would appear to tilt and you'd start to see them at an angle. The farther north or south you went, the more of the ring plane would become visible, and the rings would appear wider and brighter. If you travelled all the way to Saturn's poles, you'd be looking down on the rings from above, and they'd appear as enormous circular disks surrounding the planet. But the most spectacular views would be from latitudes somewhere in between, where the rings would arch across the sky at a dramatic angle. From these vantages, the rings would be a dominant feature of the sky, far more prominent than the moon appears from Earth. They'd cast shadows on the planet during the day, creating bands of darkness that would move across the surface as Saturn rotated, and at night the rings would reflect sunlight down onto the planet, creating a soft, diffuse illumination that would make the nighttime much brighter than it would otherwise be. Of course, this is all speculation, because we can't actually stand on Saturn's surface, but it's a useful thought experiment because it helps us appreciate the scale and beauty of the rings from a different perspective. The rings are not just something to look at from a distance. They're an integral part of Saturn's environment, affecting the planet's climate, its atmosphere, and even the appearance of its sky. Let's consider now the role that the rings play in Saturn's overall system of moons. Saturn has more than 80 known moons, ranging from tiny moonlets just a few kilometers across to giant Titan, which is larger than the planet Mercury. Many of these moons orbit outside the rings, but some orbit within or very close to the ring system, and these moons have a special relationship with the rings. We've already talked about shepherd moons like Prometheus and Pandora, which orbit on either side of the F-ring and help maintain its structure. There are other small moons embedded within the rings themselves, like Pan in the Encke Gap and Daphnis in the Keeler Gap. These moons are too small to be seen easily from Earth, but they were discovered by careful analysis of the structures they create in the rings. The gaps they carve out are much wider than the moons themselves because the moon's gravity affects particles over a large region. There are also larger moons that orbit just beyond the outer edge of the rings. These moons, like Mimas, Enceladus, and Tethys, interact with the rings through gravitational resonances. Even though they're far from the rings, their gravity can reach across the empty space and affect particles at specific distances where the orbital periods match up in simple ratios. These resonances are what create some of the gaps and divisions in the rings, like the Cassini division, which is partly cleared out by a resonance with Mimas. The relationship between the moons and the rings is a two-way street. The moons shape the rings, but the rings also affect the moons. When a moon passes close to the rings, the gravity of all those particles can tug on the moon, changing its orbit slightly. Over long timescales, these tugs can cause the moon's orbit to evolve, drifting inward or outward, becoming more or less eccentric. This orbital evolution is an important process in the Saturn system, and it helps explain the current configuration of moons and rings. Some scientists think that the rings might even be a source of new moons. If particles in the outer parts of the rings manage to clump together and stick, they could gradually build up into larger and larger objects, eventually forming moonlets and then full-sized moons. This process would take a very long time, but it's possible that some of Saturn's small moons formed this way, accreting from ring material over millions of years. On the other hand, moons can also be a source of ring material. If a moon wanders too close to Saturn and crosses the Roche limit, it can be torn apart by tidal forces, and the debris becomes part of the rings. Or if a moon is hit by a comet or asteroid, the impact can shatter the moon and spread fragments into orbit. These processes can create new rings, or add material to existing rings, and they show that the ring system is not static but constantly changing in response to the dynamics of the moon system. Now let's think about the future of Saturn's rings. What will happen to them over the next millions and billions of years? Will they persist, or will they gradually fade away? The answer depends on several factors, including the rate at which material is being lost from the rings, the rate at which new material is being added, and the processes that shape and maintain the ring structure. As we mentioned earlier, The Cassini mission found that material is falling from the rings into Saturn's atmosphere at a significant rate. If this rate continues unchanged, the rings could be depleted in a few 100 million years. But it's not clear whether the loss rate will stay constant. It might slow down as the rings become less dense, or it might speed up if the remaining particles become more susceptible to being swept out of the rings by the magnetic field, or by passing moons. At the same time, new material might be added to the rings by impacts on Saturn's moons. Every time a meteoroid hits one of the icy moons, it kicks up a spray of ice particles, and some of those particles might escape from the moon and join the rings. The rate of this process depends on the flux of meteoroids in the Saturn system, which probably varies over time as Saturn moves through different regions of the solar system and encounters different populations of debris. It's also possible that the rings could be replenished catastrophically by a major impact or by the breakup of a moon. If a moon were to be shattered by a collision or torn apart by tidal forces, the resulting debris could add a huge amount of material to the rings all at once, potentially making them brighter and more extensive than they are now. This kind of event might happen only once every few 100 million years, but when it does, it could reset the clock on the ring's lifetime. Another factor that could affect the future of the rings is the gradual evolution of Saturn's rotation and magnetic field. Saturn spins very fast. It completes one rotation in just over 10 hours, and this rapid rotation affects the shape of the planet and the structure of its magnetic field. Over billions of years, Saturn's rotation might slow, down due to tidal interactions with its moons, and this could change the way the magnetic field interacts with the rings and the way material is transported between the rings and the atmosphere. In the very long term, the rings might not survive at all. If the loss rate exceeds the input rate, the rings will eventually be depleted and Saturn will lose its most iconic feature. On the other hand, if new rings can form from time to time through moon breakup or major impacts, then Saturn might always have rings, even if the specific configuration changes over time. We might be living during a period when Saturn happens to have particularly bright and extensive rings, or we might be seeing a typical state that Saturn has maintained for much of its history. Without more data, it's hard to say for sure. What we can say is that the rings are a dynamic, evolving system, and their future is uncertain. They're not a permanent fixture of the solar system, but a transient phenomenon, something that exists for a while and then changes or disappears. This makes them all the more precious and remarkable, a reminder that even the grandest structures in nature are subject to change, and that everything we see today is just a snapshot of a much longer story. Let's think now about what the rings can teach us about physics and about the universe in general. The rings are, in many ways, a natural laboratory for studying processes that occur on much larger scales. The way particles interact in the rings is similar to the way stars interact in galaxies, or the way gas and dust interact in the disks around young stars. By studying the rings up close, we can learn about these larger-scale processes in a controlled and accessible environment. For example, the spiral density waves in Saturn's rings are very similar to the spiral arms in galaxies. In both cases, the waves are created by gravitational interactions, and they propagate through a disk of material, creating patterns that rotate and evolve over time. By studying how these waves behave in the rings, where we can see them in great detail and measure their properties precisely, we can test theories about how spiral arms form and persist in galaxies, where the scales are much larger and the observations are much more difficult. The rings also provide insights into the process of accretion, which is how planets and moons form from smaller pieces. In the rings, we can see particles colliding, sticking together temporarily, and then breaking apart again. We can measure how these processes depend on the size and speed of the particles, on the temperature and composition of the material, and on the gravitational environment. All of this information helps us understand how planets formed in the early solar system. When the space around the young sun was filled with a disk of gas and dust that gradually coalesced into the planets we see today. The rings are also a testing ground for ideas about chaos and order in dynamical systems. The motion of individual particles in the rings is, in principle, completely deterministic. If you know the position and velocity of a particle at one time, you can calculate where it will be at any future time. But in practice, the motion is so sensitive to small changes that it becomes effectively unpredictable. A tiny nudge from a collision or a gravitational interaction can send a particle on a completely different path, and over time, the The cumulative effect of all these small nudges makes the system chaotic, and yet despite this chaos at the level of individual particles, the rings as a whole show remarkable order and structure. The gaps and divisions are sharp and well defined, the spiral density waves are regular and periodic, and the overall appearance of the rings is stable over timescales of years or even decades. This coexistence of chaos and order is a fundamental feature of many complex systems, from the rings of Saturn to the weather on Earth to the behavior of financial markets, and studying the rings helps us understand how order can emerge from chaos. Now let's take a moment to appreciate the sheer beauty of the rings from an aesthetic perspective. There's something deeply satisfying about the elegance and simplicity of the ring structure. The rings are just particles following orbits, governed by gravity and shaped by collisions, but the result is a form that's both simple and intricate, both regular and varied. The rings have a kind of minimalist beauty, like a piece of abstract art where the power comes from the purity of the form. The colours of the rings add to their beauty. While the rings are mostly white and grey, there are subtle variations in tone and hue that create depth and interest. Some regions are almost pure white, gleaming in the sunlight, while others have a slightly warmer tone, hinting at the presence of impurities or different types of ice. In backlit images, the rings take on a golden or amber glow, with light streaming through the gaps and creating halos around the denser regions. The play of light and shadow, the contrast between bright and dark, the delicate gradations of tone, all of these contribute to the visual impact of the rings. There's also a certain poetry to the rings, a sense of grace and motion that comes from the way they turn around Saturn. The rings are not static, they're in constant motion, with particles orbiting at different speeds and creating waves and ripples that propagate through the system. But the motion is so smooth and so slow, at least from our perspective, that it looks almost like a dance, a choreographed performance where every particle knows its place and moves in perfect harmony with its neighbours. The rings also have a kind of fragility that makes them poignant. They're so thin and delicate, and they're constantly being eroded by collisions and by material falling into Saturn. They might not last forever, and in cosmic terms they might be gone, in the blink of an eye. This transience makes them all the more valuable, a reminder to appreciate beauty while it lasts and to recognise that everything in the universe is temporary. Let's end by bringing things back to a human scale, thinking about what the rings mean to us and why they matter. The rings of Saturn have fascinated people for centuries, ever since they were first glimpsed through early telescopes. They've inspired artists and poets, scientists and dreamers, and they've become one of the most iconic images in all of astronomy. When you see a picture of Saturn with its rings, you immediately recognise it, and you feel a sense of wonder and awe. Part of the appeal is the sheer alienness of the rings. There's nothing like them on Earth, nothing in our everyday experience that prepares us for the sight of a giant planet surrounded by a shining disk of ice. The rings remind us that the universe is full of wonders, full of things that are strange and beautiful and beyond our imagination. They expand our sense of what's possible and challenge us to think beyond the familiar. But the rings also have a kind of accessibility. Unlike distant galaxies or black holes, the rings are something we can actually see and study in detail. We've sent spacecraft to visit them, we've taken close-up pictures, and we've measured their properties with precision. We can understand how they work, at least in broad terms, using the same physics that governs motion and gravity on Earth. The rings are exotic, but they're not incomprehensible, and that makes them a perfect subject for exploration and discovery. The rings also connect us to the history of science, and to the long tradition of observation and inquiry that has brought us to our current understanding of the universe. When Galileo looked at Saturn through his telescope and saw something strange but couldn't quite make out what it was, he was taking part in the same process of discovery that continues today. Each generation of scientists is built on the work of those who came before, using better instruments and better theories to peel back the layers of mystery and reveal the rings in ever greater detail. And the story isn't over. There's still a lot we don't know about the rings, still questions to answer and mysteries to solve. How old are they? How did they form? How long will they last? What can they tell us about the early solar system and about the processes that shape planetary environments? Every new observation, every new mission brings us closer to the answers, but there's always more to learn. For now, though, we can simply rest in the knowledge that the rings are there, turning slowly around Saturn, catching the sunlight and scattering it back into space. They're a reminder of the beauty and complexity of the natural world, of the way simple rules can create intricate patterns, and of the deep connection between motion and gravity, between chaos and order. They're a source of wonder and inspiration, a testament to the power of curiosity and the joy of discovery. As you drift off to sleep tonight, you can picture the rings in your mind, pale and bright against the darkness of space, each particle following its own quiet path, each one part of a larger whole. You can imagine yourself floating among them, weightless and peaceful, watching the slow turn of the system and feeling the gentle pull of gravity. You can let the image fill your mind, pushing out all the worries and distractions of the day, and you can sink into the calm, steady rhythm of the orbits. The rings don't rush, and neither do you. There's no hurry, no pressure, no need to do anything but rest. The particles are content to orbit forever, and you can be content to let go, to relax, to drift into sleep. Your thoughts can become like the particles, light and separate, each one floating on its own path, gently bumping into others and bouncing away, until they all settle into a quiet, harmonious pattern. Take a slow breath in, filling your lungs with calm, and then let it out slowly, releasing any tension. Imagine that with each breath you're becoming lighter, more relaxed, more like the ice particles drifting in the rings. You're held in the gentle embrace of gravity, not falling but floating, moving in a perfect circle that brings you around again and again to the same peaceful place. The rings are still there, shining in the sunlight, and they'll be there tomorrow and the next day and for millions of years to come. They don't need you to watch them or think about them. They're fine on their own, turning in their quiet orbits. And you're fine too, safe and warm, ready to rest, ready to let go of the day and drift into sleep. So let yourself go now. Let your mind become light and airy. Let your body sink into the bed. Let the images of the rings fade into a soft, comfortable darkness. You don't need to think anymore. You don't need to analyze or understand. You just need to be, to exist in this moment, to rest in the knowledge that everything is all right. The rings are orbiting, your breath is flowing, and sleep is coming, gentle and inevitable, like the slow turn of particles around a giant planet. You're part of the same universe, following the same laws, held in the same balance of forces, and as the rings drift through space, you drift through sleep, peaceful and still, until the morning light brings you back again. The next story is about to begin. Please relax and enjoy. Cannabis is a flowering plant that humans have noticed, used, and studied for a very long time. When we say this, we mean truly a very long time. Thousands of years, stretching back into periods of history where written records fade into archaeology and conjecture. The plant itself is quite ordinary in some ways, belonging to a family of flowering plants that includes other species you might never associate with it. It grows from seed, reaches towards sunlight, produces leaves and flowers, and completes its life cycle in a rhythm that mirrors countless other plants across the planet. Yet despite this ordinariness, cannabis has attracted sustained human attention across cultures, climates, and centuries, becoming woven into the fabric of agriculture, medicine, ritual, industry, and law in ways that few other plants can claim. The word marijuana is a common name for cannabis, especially in everyday conversation. You'll hear it in news reports, casual discussions, policy debates, and medical contexts. The term itself carries interesting historical weight. It entered English usage primarily through Mexican Spanish in the early 20th century, and its adoption in the United States became intertwined with particular political and cultural narratives. But for our purposes tonight, as we settle into a calm exploration, we can simply acknowledge that marijuana and cannabis refer to the same botanical reality, even if the words carry different connotations depending on who's speaking and when. Language is like that, never perfectly neutral, always shaped by time and place, but ultimately pointing toward the same green, growing thing. In science writing, you'll often see the plant discussed as cannabis sativa, cannabis indica, or as mixtures and varieties of both. These names follow the binomial nomenclature system that Carl Linnaeus developed in the 18th century, a method of naming living things that gives each organism a two-part Latin name, a genus and a species. Cannabis is the genus. Sativa and indica are traditionally considered species or subspecies. though modern genetic analysis has made these distinctions somewhat murkier than they appeared in earlier botanical texts. Sativa in Latin means cultivated, reflecting the long history of human cultivation of this plant. Indica refers to India, where certain varieties were identified and described by European botanists. In practice, most cannabis today represents hybrids, plants bred from multiple genetic lineages over many generations, so the old categories have become more like general descriptive labels than strict biological divisions. But the names persist, partly because they are embedded in culture, commerce, and casual conversation, and partly because they still gesture toward real, if complex, patterns in plant characteristics. Cannabis is known for producing a family of natural compounds called cannabinoids. This is perhaps the most scientifically distinctive thing about the plant. Cannabinoids are a class of chemical compounds, and while they're not unique to cannabis in an absolute sense, some cannabinoid-like molecules have been found in other plants, and the human body even makes its own. The cannabis plant produces them in unusual abundance and variety. Scientists have identified well over 100 different cannabinoids in cannabis, each with its own molecular structure and potential effects. These compounds are synthesized within the plant as part of its natural chemistry, likely serving various functions in the plant's own life, perhaps deterring herbivores, protecting against UV radiation, or playing roles in reproduction and growth that we're still working to fully understand. For humans, though, cannabinoids have become objects of intense interest because of the ways they can interact with our own biology, particularly with receptor systems in our nervous and immune systems. The plant also produces aromatic molecules called terpenes, which contribute to its scent. If you've ever walked past a pine tree and noticed that sharp, clean, resinous smell, or peeled an orange and been struck by the bright citrusy aroma, you've experienced terpenes. These are volatile organic compounds, small molecules that evaporate easily and carry scent through the air. Cannabis produces dozens of different terpenes, and the specific blend varies from one variety to another, creating a wide palette of possible aromas. Some cannabis smells earthy and musky, others sweet and fruity, still others sharp and herbal. The terpenes are made in the same tiny structures that produce cannabinoids, and while they're often discussed separately, they exist together in the living plant, mingling in complex chemical cocktails that give each variety its unique sensory signature. Terpenes aren't just about smell either. Many have been studied for their own potential biological activities, though the science there is still developing and often less clear than the cannabinoid research. Cannabis is wind-pollinated, meaning it can rely on air movement rather than insects to move pollen. This is worth pausing on for a moment because it tells us something about the plant's reproductive strategy. Many flowering plants depend on pollinators, bees, butterflies, birds, and so on, and have evolved showy flowers, sweet nectar, and enticing scents to attract these animal partners. Cannabis, by contrast, produces relatively inconspicuous flowers and releases clouds of lightweight pollen into the air, trusting the wind to carry those pollen grains to receptive female flowers on other plants. This approach is common in grasses and many trees, and it reflects a different ecological bet. Instead of investing energy in attracting specific pollinators, the plant produces abundant pollen and lets probability and air currents do the work. For human cultivators, this has practical implications. Male plants can pollinate females from surprising distances if the wind is right, which is why growers who want seedless flowers often go to great lengths to exclude male plants or grow only feminized varieties. The plant's flowers are where many of its notable compounds concentrate. Technically, we're talking about the female flowers, which in cannabis can be dense, resin-coated clusters of small blooms. These structures, sometimes called buds or colas, are where the trichomes, those tiny glandular outgrowths, are most abundant. Trichomes look like tiny mushrooms or lollipops under magnification, and they're the primary factories for cannabinoid and terpene synthesis. When people discuss the potency or aroma of a particular cannabis variety, they're usually referring to the chemical content of these flowers. The concentration of compounds can vary based on genetics, growing conditions, timing of harvest, and post-harvest handling. In the wild, these flowers would eventually be pollinated, produce seeds, and complete the plant's reproductive cycle. In cultivation for cannabinoid production, growers typically prevent pollination to keep the flowers seedless and maximize resin production, a practice that has shaped modern cannabis genetics and culture in significant ways. Cannabis has been used for different purposes across history, including fiber, seed, and its chemistry. The fiber use is ancient. Cannabis stems contain strong, long fibers that can be separated and woven into textiles, rope, and paper. This is the same plant, botanically speaking, though varieties bred for fiber production, often called hemp, are typically low in THC and selected for tall, straight growth. The seeds are nutritious, containing proteins, essential fatty acids, and minerals, and have been used as food and pressed for oil in many cultures. Meanwhile, the flowers and leaves have been used for their chemical effects in medicine, ritual, and recreation, practices that also extend back thousands of years. This multiplicity of uses has meant that cannabis has travelled with humans, been cultivated in diverse climates, and adapted to various agricultural systems, accumulating a complex cultural and economic history that intersects with colonialism, trade, medicine, and law in tangled ways. Tonight, though, we can simply note this richness without needing to untangle every thread. Today, cannabis is discussed in science, medicine, law, and culture, often all at once. Open a newspaper or a scientific journal, and you might find articles about clinical trials testing cannabinoids for epilepsy, debates about legalization and regulation, discussions of social justice and the impacts of prohibition, or profiles of emerging cannabis industries. This simultaneity can make cannabis feel like an unusually charged topic, but in some ways it's just a vivid example of how complex any significant topic becomes when you look closely. Every plant that humans care about, wheat, corn, rice, coffee, tobacco, has its own layered story involving botany, chemistry, culture, economics, and politics. Cannabis happens to be at a particularly dynamic moment in that story, with rapid changes in legal status, medical research, and public perception all happening at once in many parts of the world. For someone trying to understand cannabis calmly and clearly, this can feel overwhelming, but it can also be an invitation to slow down and look at one layer at a time. For bedtime, we can treat it like a calm museum exhibit, a plant, a chemistry set, and a long story. Imagine walking through a natural history museum late at night, when the crowds have gone home and the galleries are quiet. You come to an exhibit about cannabis. There's a botanical specimen behind glass, carefully labelled diagrams showing its anatomy, glass vials containing purified cannabinoids, charts illustrating receptor systems in the human body, and historical artifacts showing its many uses. The lighting is soft, this information is clear, and there's no pressure to rush through or form strong opinions. You can simply observe, learn a little, and move on when you're ready. That's the spirit in which we can approach these facts tonight, not as a debate to win or a mystery to solve, but as a quiet, unhurried tour through interesting territory. Let the information settle gently, and let your mind remain calm and curious without strain. Now we'll drift from the big label cannabis into the gentle details of the plant itself, its structure, its life cycle, and its quiet botany. Cannabis is an annual plant, meaning it completes its life cycle within a single growing season. From the moment a seed germinates in spring, through vegetative growth in the lengthening days of early summer, into flowering as the days shorten in late summer and autumn, and finally to seed production and senescence as winter approaches. The whole drama unfolds in roughly 6 to 10 months depending on variety and climate. This annual rhythm is common among many flowering plants, and it's shaped by the plant's sensitivity to day length and temperature. Unlike perennial plants, which can live for years or even centuries, cannabis invests everything in a single reproductive push each year, producing as many seeds as possible before dying back. For human cultivators, this annual cycle has advantages. It allows for selective breeding and experimentation from one generation to the next in a relatively short time frame, but it also means the plant must be started fresh each year from seed, or, in some cases, from clones of a mother plant kept alive artificially. Like many flowering plants, it has roots, stems, leaves, and reproductive structures. This might seem too basic to mention, but there's something soothing about returning to fundamentals. The roots anchor the plant and absorb water and nutrients from the soil, extending downward and outward in patterns that can mirror the spread of the above-ground canopy. The stem supports the plant, channels water and nutrients upward, and holds the leaves and flowers up toward the light. Cannabis stems can grow quite tall. Some varieties reach 6 feet or more, and they become woody and fibrous as the plant matures. The leaves are the photosynthesis engines, capturing sunlight and converting it into chemical energy that fuels growth. And the reproductive structures, flowers in the case of females, pollen sacs in males, carry out the plant's ultimate biological purpose, creating the next generation. Each part is connected, each part necessary, each part operating according to the same principles that govern plant biology everywhere. Cannabis leaves are often palmate, meaning they spread like fingers from a central point. If you've seen pictures of cannabis, you've almost certainly noticed its distinctive foliage. The leaves typically have serrated edges and anywhere from 3 to 13 leaflets radiating from a central stem, though 5 to 9 is most common. This palmate arrangement is efficient for light capture. The leaflets spread out to maximize surface area without excessively shading each other, and it's also visually distinctive, making cannabis leaves recognizable even in silhouette. Young plants start with simpler leaves, often just a single or 3 leaflets, and as the plant grows and matures, the leaves become more complex. Later in the plant's life, as it shifts toward flowering, the leaves may again simplify, with fewer leaflets and smaller overall size. This progression is part of the plant's developmental program, a genetically encoded sequence that unfolds predictably under the right conditions. The plant produces trichomes, tiny resin-like structures that can look like a fine frost. If you examine a mature cannabis flower closely, ideally with a magnifying glass or microscope, you'll see what appears to be a crystalline coating, a dense carpet of tiny translucent or milky structures. These are the trichomes, and they come in several types. The most conspicuous are the capitate stalked trichomes, which have a rounded head atop a slender stalk. There are also smaller sessile trichomes and non-glandular trichomes, each with different structures and functions. The glandular trichomes are where the cannabinoid and terpene synthesis happens in specialized cells within the trichome head. Under the right lighting, trichomes can sparkle and shimmer, giving the flowers a frosted or jeweled appearance. This visual quality has become aesthetically significant in cannabis culture, with dense trichome coverage often taken as a sign of potency or quality, though the relationship between visible trichomes and actual cannabinoid content is complex and requires chemical testing to verify. Trichomes are one place where cannabinoids and terpenes are produced and stored. The cells inside the trichome heads contain the enzymatic machinery necessary to synthesize these complex molecules from simpler precursors. The process begins with basic building blocks like amino acids and simple sugars, which are combined and modified through multiple chemical steps, each catalyzed by a specific enzyme encoded in the plant's DNA. The cannabinoids are synthesized in their acidic forms, TH, CA, CBDA, and so on, and stored in the trichome heads along with terpenes and other secondary metabolites. This storage function is important because these compounds can be sticky and potentially toxic to the plant's own cells in high concentrations, so sequestering them in specialized structures makes biochemical sense. The trichomes essentially serve as both factory and warehouse, producing and holding the chemicals until the plant is harvested, at which point heat, light, and time begin to transform them into their more familiar neutral forms. Cannabis plants can be dioecious, meaning male and female flowers grow on separate plants, though other patterns can exist too. Dioecy is relatively uncommon in the plant kingdom. Most flowering plants are hermaphroditic, producing both male and female structures on the same plant or even in the same flower. Cannabis, however, typically produces male plants that make pollen and female plants that produce flowers capable of being fertilized. This separation has evolutionary implications related to genetic diversity and outcrossing, encouraging pollen from one plant to fertilize flowers on another, rather than allowing self-fertilization. In practice, though, cannabis sexuality is more flexible than strict dioecy would suggest. Environmental stress, particularly late in the flowering period, can sometimes induce female plants to produce male flowers, a phenomenon that ensures seed production even in the absence of male plants. There are also hermaphroditic varieties and plants that show mixed sexual expression. For cultivators, this flexibility can be a blessing or a curse, useful for ensuring pollination when desired, but a problem when trying to maintain seedless flowers. Female flowers are often the focus in discussions of cannabinoids because they can be especially resin-rich. When a female flower is not pollinated, it continues to produce trichomes and accumulate cannabinoids and terpenes, possibly as a continued attempt to attract pollen, or perhaps as a defense against herbivores and pathogens. This unpollinated state is what growers seek when cultivating cannabis for cannabinoid content, and the resulting seedless flowers are called sin semilla, a Spanish term meaning without seed. The concentration of cannabinoids in these flowers can be much higher than in leaves or stems, which is why flowers are the primary harvest in medical and recreational production. The specific cannabinoid profile depends on genetics, but environmental factors like light, temperature, nutrients, and stress can also influence the final chemistry. Harvest timing matters too. Cannabinoid levels peak at a certain point in flower. Maturity and harvesting too early or too late can affect both quantity and quality of the desired compounds. Male plants produce pollen, which can fertilize female flowers and lead to seed formation. From a botanical perspective, this is the whole point: the male's role in the sexual reproduction cycle. Each pollen grain is a microscopic package containing the male genetic contribution, and when conditions are right, these grains are released in great numbers and carried on the wind. If a pollen grain lands on a receptive female flower, it germinates, grows a tube down into the ovary, and delivers its genetic material to unite with the female's contribution. The resulting embryo develops into a seed, a compact package containing a new plant's genetic blueprint, along with stored nutrients to fuel its initial growth. For cultivators focused on cannabinoid production, male plants are often unwanted, as pollination shifts the female plant's energy away from resin production and toward seed development. But for breeders, males are essential. They're half of every genetic cross, and selecting the right males is as important as selecting the right females when developing new varieties. The seeds of cannabis can be used as a food source in some contexts because they contain oils and nutrients. Cannabis seeds are rich in protein, containing all 9 essential amino acids in significant quantities. They also provide essential fatty acids, including omega-3 and omega-6 in favourable ratios, as well as minerals like magnesium, phosphorus, and potassium. In some cultures, cannabis seeds have been eaten whole, pressed for oil, or ground into meal for use in cooking. The seeds contain negligible amounts of THC or other intoxicating cannabinoids. Those compounds are concentrated in the flowers and trichomes, not in the seeds themselves, so they can be consumed without psychoactive effects. Hemp seed oil, pressed from varieties bred for low THC content, has been used both as a food oil and in industrial applications like paints and cosmetics. The nutritional profile has made hemp seeds a niche product in health food markets in some countries where cannabis cultivation is permitted under specific regulations. Seen purely as botany, cannabis is simply one more creative expression of plant biology. It photosynthesizes using the same chlorophyll machinery as lettuce and sunflowers. It responds to the same hormonal signals, auxins, gibberellins, cytokinins, that govern growth and development across the plant kingdom. Its flowers follow the same basic anatomical plan as countless other flowering plants, with sepals, petals, though reduced in cannabis, stamens and pistils arranged according to ancient evolutionary templates. What makes cannabis distinctive is not that it breaks botanical rules, but rather that it produces an unusual abundance of particular secondary metabolites that happen to interact in interesting ways with mammalian nervous systems. That interaction is what has driven so much of the human interest in this plant. But from the plant's perspective, it's just doing what all plants do: growing, reproducing, responding to its environment, and producing chemicals that help it survive and thrive in its ecological niche. With the plant's shape in mind, we can step into its chemical vocabulary, the cannabinoids that make cannabis scientifically distinctive. Cannabinoids are a group of natural compounds that can interact with certain systems in the human body. To understand what this means, we need to think about how cells communicate. Human bodies are made up of trillions of cells, and these cells need to coordinate their activities to maintain health and respond to changing conditions. They do this partly through chemical signaling. One cell releases a molecule that travels to another cell, where it binds to a receptor protein, triggering a response inside that second cell. This is the basic logic of neurotransmitters, hormones, and many drugs. Cannabinoids from the cannabis plant are shaped in such a way that they can fit into certain receptor proteins in the human body, particularly ones called cannabinoid receptors, and when they do, they can trigger or block various cellular responses. This key and lock mechanism is why cannabinoids have biological effects in humans and other animals. Cannabis produces many cannabinoids, not just one or two. early cannabis research often focused on just a handful of compounds, particularly THC, but as analytical chemistry has improved, scientists have identified a much broader spectrum. Some cannabinoids are present in high concentrations in certain varieties, while others appear only in trace amounts. Some have been studied extensively in laboratories and clinical trials, while others remain poorly understood, their effects known only from preliminary cell studies or speculation. This diversity exists because the plant's biosynthetic pathways can produce many variants on the basic cannabinoid structure, with different enzymes making small modifications, adding a chemical group here, removing one there, that create a whole family of related but distinct molecules. From a research perspective, this chemical diversity is both exciting and challenging. Exciting because it suggests many potential therapeutic applications, challenging because it makes the science more complex and time-consuming to work through systematically. Two of the most discussed cannabinoids are THC and CBD. These are the stars of most cannabis conversations, the ones that appear in product labels, news articles, and medical studies. They're not the only important cannabinoids, but they're the ones that have been studied most and that are produced in the highest concentrations in many cannabis varieties. THC and CBD have different effects, different legal statuses in many jurisdictions, and different profiles of medical interest, which has made them the focus of separate research programs and commercial development efforts. Understanding these two molecules, what they are, how they work, and how they differ, is a good foundation for making sense of cannabis more broadly. THC is short for tetrahydrocannabinol. More precisely, it's delta-9 tetrahydrocannabinol, often written as delta-9 THC, though there are also other THC variants like delta-8 tetrahydrocannabinol that differ slightly in their molecular structure. The name itself is descriptive. Tetrahydro indicates 4 added hydrogen atoms in the molecule's structure, and cannabinol places it in the cannabinoid family. THC is what's called a partial agonist at cannabinoid receptors, particularly the CB1 receptor, meaning it binds to these receptors and activates them, but not as strongly as a full agonist would. This partial activation is part of what gives THC its particular profile of effects, strong enough to produce noticeable changes in perception and cognition, but with a ceiling that limits the intensity compared to some synthetic cannabinoids that have been developed. CBD is short for cannabidiol. Unlike THC, CBD does not strongly activate CB1 receptors, which is why it doesn't produce the typical intoxicating effects associated with cannabis use. Instead, CBD's mechanism of action is more diffuse and less completely understood. It appears to interact with multiple receptor systems, including some serotonin receptors, adenosine receptors, and receptors involved in pain signaling and inflammation. It may also influence cannabinoid receptors indirectly, modulating the effects of endocannabinoids, the body's own cannabinoid-like molecules, rather than strongly activating the receptors itself. This complex pharmacology has made CBD an interesting target for medical research, with studies exploring its potential in conditions like epilepsy, anxiety, and chronic pain. Though the strength of evidence varies considerably by condition, cannabinoids in the plant often begin in acidic forms like THCA and CBDA, before changing through heat or time. This is an important detail that's sometimes overlooked in casual discussions. When cannabis is growing and freshly harvested, the cannabinoids are primarily in their acidic forms, THCA, CBDA, CBGA, and so on. These molecules have an extra carboxyl group, a carbon atom bonded to 2 oxygen atoms, which changes their shape and properties. THCA, for instance, is not intoxicating because it doesn't fit well into CB1 receptors. It's only when the plant material is heated, through smoking, vaporization, or cooking, that a chemical reaction called decarboxylation occurs. The heat breaks off the carboxyl group, releasing it as carbon dioxide and leaving behind the neutral form, THC from THCA, CBD from CBDA. This transformation is why raw cannabis doesn't produce intoxication if eaten, but cannabis that's been heated does. The acidic forms may have their own biological activities. There's some research into THCA and CBDA as distinct compounds, but they're less well studied than their neutral counterparts. Different cannabis varieties can have very different cannabinoid profiles. This is one of the most important things to understand about cannabis chemistry. There's no single cannabis content. Some varieties, often called strains, produce high levels of THC and low levels of CBD. Others produce high CBD and low THC. Still others produce more balanced ratios, or emphasize minor cannabinoids like CBG or CBN. These differences arise from genetics. Different varieties carry different versions of the genes that encode the enzymes responsible for cannabinoid synthesis, and they can be dramatic. A variety bred for medical CBD use might contain 20% CBD and less than 1% THC by dry weight, while a variety bred for recreational use might contain 20% THC and negligible CBD. This variability means that generalizations about cannabis effects can be misleading. The effects depend critically on which cannabinoids are present and in what amounts. Scientists use lab testing to measure cannabinoid amounts rather than relying on appearance or names. Visual inspection might tell you something about trichome density or overall plant health, but it cannot reliably predict cannabinoid content. Even the traditional variety names, often evocative terms like Northern Lights or Sour Diesel, offer no guarantee of chemical consistency, as different growers may cultivate plants under the same name with different results. Modern testing laboratories use techniques like high-performance liquid chromatography or gas chromatography, methods that separate and quantify individual cannabinoids with precision. A typical lab report might list THC, THCA, CBD, CBDA, CBG, CBN, and several others, providing percentages or milligrams per gram for each. This kind of data is essential for medical use, where consistent dosing matters and increasingly important in regulated markets where accurate labeling is required by law. Cannabinoid science sits at the intersection of botany, chemistry, neuroscience, and medicine. This interdisciplinary nature is part of what makes the field interesting, and also part of what makes it complex. To fully understand cannabinoids, you need to know something about plant biochemistry, how the molecules are made. You need analytical chemistry to measure them, organic chemistry to understand their structures and reactions, pharmacology to study how they interact with biological systems, neuroscience to explore their effects on the brain and nervous system, and medicine to translate all of that into potential treatments for disease. Each discipline brings its own tools, terminology, and perspectives, and breakthroughs often come when insights from one field inform work in another. The result is a rich and rapidly evolving scientific literature that can be challenging to navigate but also rewarding for anyone willing to engage with it carefully. It can feel soothing to remember. This is chemistry doing what chemistry does, quietly, predictably, and lawfully. The cannabinoids aren't magical or mysterious. They're molecules made of carbon, hydrogen, and oxygen, obeying the same physical laws as every other molecule in the universe. Their effects on the human body are the result of specific, measurable interactions between molecular shapes and protein structures. Science can study these interactions, measure them, map them, and over time come to understand them in ever greater detail. There will always be uncertainty at the edges. Biology is complex and individual variation is real. But the fundamental mechanisms are knowable and in many cases already known. This is the opposite of mystery. It's the deep, calm certainty that comes from recognizing that nature follows rules, and those rules can be learned. Next, we'll slow down and compare THC and CBD in a gentle, neutral way. Two molecules often mentioned together but not identical in effects. THC is the cannabinoid most associated with intoxication or a high. This is the compound that most people are referring to when they talk about getting high from cannabis. When THC binds to CB1 receptors in the brain, it alters the normal signaling patterns in neurons, particularly in areas involved in memory, time perception, coordination, and pleasure. The subjective experience varies widely from person to person and context to context, but common reports include changes in sensory perception, altered time sense, euphoria or relaxation, increased appetite, and sometimes anxiety or paranoia. The intoxication is generally self-limiting. It peaks within an hour or two after inhalation and gradually fades over the next few hours, and for most people it's not dangerous in a physical sense, though it can be unpleasant or distressing if the dose is too high or the setting is uncomfortable. THC affects perception and can change how time, attention, and sensation feel for some people. The time distortion is a particularly consistent feature. Minutes can feel longer, and tasks that normally take a predictable amount of time may seem to stretch out. This effect likely arises from THC's influence on the brain regions involved in timing and sequencing, particularly the hippocampus and prefrontal cortex. Attention can become more diffuse, making it harder to focus on a single task, but sometimes easier to notice peripheral details or make loose associations between ideas. Sensory experiences, taste, sound, colour, may seem more vivid or interesting, though whether this reflects actual enhanced perception or simply increased attention to sensory input is debated. These effects can be appealing in some contexts, listening to music, appreciating art, socializing, but they can interfere with tasks that require sustained attention, quick reactions, or precise timing, which is why impairment is a concern for activities like driving. CBD is not typically intoxicating in the same way THC is. People who take CBD, even in substantial doses, generally do not report feeling high. They remain clear-headed, their perception of time doesn't distort, and their coordination isn't obviously impaired. This difference is rooted in CBD's mechanism of action. Because it doesn't strongly activate CB1 receptors in the brain, it doesn't trigger the cascade of neural changes that produces the THC-type intoxication. This property has made CBD attractive for medical applications, where patients need symptom relief without impairment, and it's also allowed CBD products to occupy a different legal and cultural space than THC products in many jurisdictions. That said, CBD is not without effects. People sometimes report feeling calmer or more relaxed, and at higher doses some people may feel mildly sedated. But these are generally described as subtle and not intoxicating in the sense of feeling altered. CBD is often studied for potential effects on anxiety, inflammation, and seizures, though results vary by condition and study design. The epilepsy research has been the most successful in producing clear, reproducible results. A pharmaceutical-grade CBD preparation called Epidiolex has been approved in multiple countries for certain rare and severe forms of childhood epilepsy, based on clinical trials showing significant reductions in seizure frequency. The anxiety research is more mixed. Some studies suggest CBD can reduce anxiety in specific contexts like public speaking, but the evidence for generalized anxiety disorder or other anxiety conditions is less robust. Inflammation research is mostly preclinical, meaning it's been done in cell cultures or animal models rather than human patients, and while the results are sometimes promising, translating those findings to actual human disease treatment is an uncertain process. The important thing is that CBD is being studied seriously, with controlled trials and careful outcome measures, and the picture that's emerging is nuanced. It seems to help some conditions more than others, and more research is needed to define where it's most useful. The same cannabinoid can have different effects depending on dose, route, and individual biology. Dose is often underappreciated in casual discussions. A low dose of THC might produce mild relaxation and subtle perceptual changes, while a high dose might produce intense disorientation and anxiety. The relationship isn't always linear. Sometimes doubling the dose more than doubles the effect, and sometimes cannabinoids show biphasic effects, where low and high doses produce opposite outcomes. Route matters too. Inhaled THC reaches the brain quickly, producing rapid onset and relatively short duration, while oral THC is metabolized in the liver and produces a slower onset, longer duration, and slightly different subjective quality because some of it is converted to a more potent metabolite. And individual biology is huge. Genetic variations in cannabinoid receptors, differences in metabolism, prior exposure and tolerance, mood, expectations, and setting all influence how a given dose will affect a given person on a given day. People can respond differently to THC based on tolerance, genetics, mood, and setting. Tolerance develops with regular use. The CB1 receptors become less sensitive or numerous, requiring higher doses to produce the same effects. This is a well-documented phenomenon, and one reason why chronic users often consume amounts that would overwhelm an inexperienced user. Genetics play a role through variations in genes, encoding cannabinoid receptors, metabolic enzymes, and neurotransmitter systems. Some people have genetic variants that make them more sensitive to anxiety from THC. Others have variants that affect how quickly they metabolize cannabinoids. Mood and mental state matter. Someone who's already anxious may be more likely to experience paranoia from THC, while someone who's relaxed and in a comfortable setting may find the same dose pleasant. The setting itself, who you're with, where you are, what you're doing, can profoundly shape the experience. a principle that psychedelic researchers have long emphasized but that applies to cannabis as well. Cannabis discussions often mention balance between THC and CBD, but balance can mean different things to different people. Some use balance to refer to roughly equal amounts of THC and CBD, a 1-to-1 ratio that's thought by some to moderate the intoxicating effects of THC, while maintaining therapeutic benefits. Others use it more loosely to mean any combination that avoids extremely high THC with negligible CBD, seeking a gentler experience. There's some evidence that CBD can modulate THC's effects, possibly by influencing how THC interacts with receptors or how it's metabolized, but the details are complex and still being worked out. In medical contexts, finding the right balance often means finding the combination that provides symptom relief with acceptable side effects for a particular patient, and that combination can vary widely. The concept is useful, but it's important to remember that it's not a precise scientific term. It's a framework for thinking about combinations, not a single correct formula. In research, careful definitions matter more than casual labels. When scientists design a study, they need to be precise about what they're testing, which cannabinoid, at what dose, delivered by what route to which population, measuring which outcomes. A study of cannabis that doesn't specify the cannabinoid content is difficult to interpret and compare to other studies. A claim that cannabis helps pain needs to be unpacked. Which type of pain? What kind of cannabis? How much? How often? Compared to what? The rigor of scientific research comes from this precision, and it's why scientific papers can seem dense and jargon-heavy. The language is trying to eliminate ambiguity. For people reading about cannabis research in popular media, it's worth being cautious about headlines that simplify these complexities. The actual studies usually reveal more nuance than the summaries suggest. In medicine, individual cannabinoids can also be studied separately from the whole plant. This is a key methodological choice. Studying a purified cannabinoid, say pharmaceutical-grade CBD, allows researchers to know exactly what dose each patient is getting, and to isolate the cannabinoid's effects from the confounding influence of other compounds. This is how modern drug development typically works, and it's how Epidiolex and synthetic cannabinoid medications like dronabinol were developed and approved. The alternative approach is to study whole plant cannabis, with its complex mix of cannabinoids and terpenes, which some argue is more relevant to how most people actually use cannabis, but which is much harder to standardize and study systematically. Both approaches have value, and they complement each other, providing different kinds of information that together build a fuller picture. The calm takeaway is that THC and CBD are simply two different keys that fit into related but not identical locks. The lock analogy is worth holding on to. Imagine a set of doors in a building. Each door leads somewhere different, and each has its own lock. THC is a key that opens certain doors, triggering certain effects. CBD is a key that opens different doors, triggering different effects. Some doors might be opened by multiple keys, some require specific keys, and some keys might partially fit but not fully turn the lock. This is not a perfect analogy. Biological systems are messier than buildings, but it captures the idea that different molecules have different actions because of their different shapes and the different receptors they interact with. There's no moral judgment here, no good key and bad key, just different tools with different purposes. Tonight, you can let that simplicity be enough. With cannabinoids softly introduced, we can wander into the world of scent. Terpenes, the airy molecules that make plants smell like themselves. Terpenes are aromatic compounds found in many plants, not only cannabis. In fact, you encounter terpenes constantly in daily life. The smell of a Christmas tree is largely due to terpenes like alpha-pinene and beta-pinene. The scent of lavender comes from linalool. The citrus aroma of orange peel is dominated by limonene. Terpenes are one of nature's largest classes of organic compounds, with tens of thousands of different structures identified across the plant kingdom. They're part of how plants defend themselves, attract pollinators, and communicate with each other and their environment. For humans, they're a major component of the sensory experience of being around plants. The reason a walk in a pine forest smells so different from a walk through a field of wildflowers, or the reason a garden full of herbs creates such a rich olfactory tapestry. Terpenes contribute to the scent of pine forests, citrus peels, lavender, and many herbs. When you peel an orange, you're rupturing tiny oil glands in the skin, releasing a burst of limonene and other terpenes into the air. When you brush against a rosemary bush, terpenes like cineol and camphor volatilize from the leaves and reach your nose. When you walk through a coniferous forest, the air is full of terpenes released by the trees, creating that characteristic fresh, resinous smell. These molecules are light enough to evaporate at room temperature, which is why you can smell them without heating or crushing the plant, though physical disruption or warmth generally increases the release. The human nose is quite sensitive to terpenes. We can detect some of them at parts per billion concentrations, and different people may perceive the same terpenes slightly differently based on variations in their olfactory receptors. Cannabis terpenes can shape its smell in ways people describe as earthy, sweet, spicy, or floral. The specific blend of terpenes in a given cannabis variety creates its aromatic signature. Some varieties smell musky and skunky, others smell sweet and fruity. Still others smell peppery or piney or like diesel fuel. These descriptions are subjective. What one person calls earthy, another might call musty. But there are patterns. Lab analysis can identify and quantify the terpenes present, and while the relationship between chemical composition and subjective smell perception is complex, there are correlations. High levels of myrcene might contribute to a musky, herbal character. Limonene might brighten the aroma with citrus notes. Caryophyllene might add a spicy, peppery edge. The total terpene content and the balance among different terpenes both matter in creating the overall impression. One common terpene is myrcene, also found in plants like hops and mangoes. Myrcene is often the most abundant terpene in cannabis, particularly in varieties described as having sedating or relaxing effects, though whether myrcene itself contributes to those effects beyond aroma is debated. It has an earthy, slightly musky smell with herbal notes, and it's present in significant amounts in hops, the plant used to flavour and preserve beer, as well as in lemongrass, thyme, and the aforementioned mangoes. In some cannabis varieties, myrcene can account for more than half of the total terpene content. There's some preclinical research suggesting myrcene might have muscle relaxant or sedative properties, but most of that work has been done in rodents or cell cultures, and whether similar effects occur in humans at the levels found in cannabis is uncertain. Another is limonene, associated with citrus-like aromas. Limonene is the second most common terpene in nature and is the dominant component of citrus peel oils. In cannabis, it contributes a bright, fresh, uplifting quality to the aroma, and some people believe it correlates with more energizing or mood-elevating effects, though again, the evidence for this is largely anecdotal. Limonene has been studied in various contexts unrelated to cannabis. It's being investigated for potential anti-cancer properties, as an aid to skin absorption of topical medications, and for antimicrobial activity. But these studies typically use purified limonene in controlled settings, not the small amounts present in cannabis. As with other terpenes, the primary confirmed role in cannabis is sensory. It shapes the smell and, when inhaled, contributes to the overall flavour profile. Pinene is linked with pine-like scents and is found in conifers and herbs. There are two main forms, alpha-pinene and beta-pinene, which differ slightly in structure and smell. Alpha-pinene has that classic sharp, fresh pine smell, while beta-pinene is a bit more woody and resinous. Both are found in turpentine, which is essentially distilled pine resin, as well as in rosemary, sage, and many other plants. In cannabis, pinene is usually present in lower amounts than myrcene or limonene, but when it is abundant, it can give the plant a distinctly herbal, forest-like quality. Some preliminary research has suggested pinene might act as a bronchodilator, opening airways, and might have anti-inflammatory properties. But as with other terpenes, much of this research is early stage and not yet translated to clear clinical applications. Linalool appears in lavender-like aromas in many botanical contexts. Linalool is perhaps best known from lavender, where it's the main component of that flower's famously calming scent. It's also found in mint, cinnamon, and more than 200 other plants. In cannabis, linalool contributes a floral, slightly spicy note to the aroma, and varieties high in linalool are sometimes described as having relaxing or calming effects. Linalool has been studied for its potential anxiolytic, anxiety-reducing properties, and there's some animal research suggesting it might have such effects, possibly through interactions with neurotransmitter systems. It's also widely used in aromatherapy, where it's thought to promote relaxation, though whether these effects are pharmacological or purely psychological is debated. In cannabis, the amounts are typically much lower than what's used in aromatherapy or clinical studies, so any direct pharmacological effect is likely to be modest at best. Terpenes may have biological effects on their own, but the science is still being refined. The challenge with terpene research is that terpenes are usually studied in isolation, at relatively high doses, often in cell culture or animal models. Showing that a terpene has an effect under those conditions doesn't automatically mean it will have the same effect in a human who inhales a small amount mixed with cannabinoids and other compounds. There's also the question of mechanism. If a terpene does have an effect, is it through direct interaction with receptors in the body, through indirect modulation of other systems, or simply through the psychological and physiological effects of smell? Smell is powerful. Certain scents can trigger memories, change mood, and even influence stress hormone levels. So it's plausible that terpenes could affect the overall experience of using cannabis partly through their aroma, even if they don't have strong direct pharmacological actions. The term entourage effect is sometimes used to suggest combined effects of compounds, though evidence and definitions vary. The idea behind the entourage effect is that cannabinoids and terpenes might work together in ways that enhance or modify their individual effects, that the whole plant is more than the sum of its parts. It's an appealing concept, and there are theoretical reasons it might be true. For instance, some terpenes might influence how cannabinoids are absorbed or metabolized, or they might act on overlapping biological pathways in ways that amplify or dampen certain outcomes. However, the evidence for a robust entourage effect in cannabis is limited. Most of the support comes from preclinical studies or from anecdotal reports by users who feel that whole plant products are more effective or have better side effect profiles than single cannabinoid products. Clinical trials directly comparing whole plant cannabis to isolated cannabinoids are rare, and the few that exist show mixed results. The term is useful as a hypothesis, but it's often invoked more loosely than the science supports. Scent, in general, is one of the gentlest senses, able to change mood without needing words. There's something almost magical about how a smell can instantly evoke a memory or shift your emotional state. The olfactory system is wired directly into the limbic system, the brain's emotional center, which is why smells can trigger such immediate and powerful responses. A whiff of a certain perfume might bring back a vivid memory of a person or place. The smell of baking bread might create a sense of warmth and comfort, and the scent of rain on dry earth might evoke a feeling of freshness and renewal. Cannabis terpenes participate in this same sensory landscape. For some people, the smell of certain cannabis varieties is pleasant and relaxing in itself, independent of any pharmacological effects. For others, it might be neutral or even off-putting. The subjective nature of scent means that the same terpene profile can be experienced very differently by different people, adding another layer of individual variability to the already complex picture of cannabis effects. Now we'll step from the plant into the body's own quiet chemistry, the endocannabinoid system, which is not for cannabis, but part of normal biology. Humans and many animals have an endocannabinoid system, often abbreviated as ECS. This is a physiological signaling system that exists in mammals, birds, reptiles, and fish. It's ancient in evolutionary terms, suggesting it serves important functions that have been conserved across species. The system was only discovered in the late 20th century, largely as a result of cannabis research. Scientists studying how THC worked in the brain identified the receptors it bound to, and then discovered that the body produces its own molecules that bind to those same receptors. The endocannabinoid system, then, is not a system designed to respond to cannabis. It's a system that cannabis happens to interact with because the plant produces molecules that mimic or modulate the body's own signaling chemicals. Endo means within, because this system uses cannabinoids made inside the body. The prefix distinguishes endocannabinoids from phytocannabinoids, cannabinoids from plants, and from synthetic cannabinoids made in laboratories. The body produces endocannabinoids on demand, synthesizing them from fatty acids in cell membranes when they're needed rather than storing them in vesicles the way many neurotransmitters are stored. This on-demand synthesis allows for rapid, localized signaling tailored to the immediate needs of specific cells and tissues. The two main endocannabinoids that have been identified are anandamide and 2-AG, though there may be others that haven't been fully characterized yet. Both are lipid molecules, fatty, greasy compounds that don't dissolve well in water, which gives them certain properties in terms of how they move through tissues and how they're synthesized and broken down. The body's own cannabinoids are called endocannabinoids. Anandamide was the first to be discovered in the early 1990s. Its name comes from the Sanskrit word ananda, meaning bliss, reflecting both the researchers' excitement at the discovery and the molecule's structural similarity to THC. Anandamide binds to cannabinoid receptors, particularly CB1, much like THC does, though it's broken down more quickly in the body and so doesn't produce as sustained an effect. The second major endocannabinoid, 2-arachidonyl glycerol or 2-AG, was identified shortly afterward. It's actually more abundant in the brain than anandamide and is thought to be the more important signaling molecule in many contexts, though both clearly play roles. These molecules are produced after a cell has been activated, for instance, after a neuron fires, and they travel backward across the synapse to bind to receptors on the sending cell, providing feedback that can modulate future signaling. This retrograde signaling is unusual and important for fine-tuning neural circuits. The ECS includes receptors, signaling molecules, and enzymes that build and break down signals. The receptors are proteins embedded in cell membranes that bind endocannabinoids and trigger intracellular responses. The signaling molecules are the endocannabinoids themselves, along with the various intracellular messengers they activate. The enzymes include the ones that synthesize endocannabinoids from membrane lipids, and critically, the ones that break them down once signaling is complete. The breakdown is important because it terminates the signal, allowing the system to reset and respond to new inputs. The main enzyme that breaks down anandamide is called FAAH, fatty acid amide hydrolase, and the main enzyme for 2-AG is MAGL, monoacyl glycerol lipase. These enzymes are themselves targets for drug development, with the idea that blocking them might increase endocannabinoid levels and produce therapeutic effects without needing to administer cannabinoids directly. Two well-known receptors are called CB1 and CB2. CB1 receptors are found primarily in the nervous system and are among the most abundant G-protein coupled receptors in the brain. They're particularly dense in areas involved in movement, memory, pain processing, and reward. CB2 receptors are found mainly in immune cells and peripheral tissues, though some are also present in the brain. For a long time, it was thought that CB1 was the brain receptor and CB2 the immune receptor. But more recent research has shown the picture is more complex, with both receptors playing roles in multiple systems and with significant overlap in their functions. There's also evidence for other cannabinoid-sensitive receptors, GPR55, GPR18, and others, though whether these should be considered part of the endocannabinoid system or separate systems is still debated. The existence of multiple receptor types helps explain why cannabinoids can have such diverse effects. They're acting on different molecular targets in different tissues. CB1 receptors are common in the brain and nervous system. They're found on the terminals of neurons, where they regulate the release of neurotransmitters. When an endocannabinoid binds to a CB1 receptor, it typically reduces the neuron's subsequent release of its neurotransmitter, whether that neurotransmitter is glutamate, GABA, dopamine, or something else. This means the endocannabinoid system acts as a kind of brake or modulator, dialing down signals that might otherwise be too strong. In areas like the hippocampus, this modulation affects memory formation and learning. In the basal ganglia, it affects movement control. In the amygdala, it affects emotional responses. The widespread distribution of CB1 receptors helps explain why THC, which activates these receptors, can have such wide-ranging effects on cognition, perception, and behavior. It's essentially hijacking a regulatory system that touches many different brain functions. CB2 receptors are more associated with immune-related tissues, though the picture is complex. They're found on immune cells like macrophages and lymphocytes, and they appear to play roles in regulating inflammation and immune responses. When CB2 receptors are activated, they can influence the release of signaling molecules called cytokines, which coordinate immune activity. This has made CB2 a target of interest for developing anti-inflammatory drugs, with the hope that activating these receptors might reduce unwanted inflammation without producing the central nervous system effects associated with CB1 activation. However, CB2 receptors are also found in some neurons, particularly in brainstem regions involved in nausea and vomiting, and their full functional significance in the nervous system is still being worked out. As with many aspects of endocannabinoid biology, the initial simple story has given way to a more nuanced and complicated reality. The ECS is involved in regulating processes like appetite, mood, memory, pain signaling, and stress responses. This is a partial list. Research has implicated the endocannabinoid system in bone formation, cardiovascular function, reproduction, sleep, and more. The common thread is homeostasis. The system seems to help maintain stability in the face of changing conditions. When you're stressed, endocannabinoids may help turn down the stress response once the immediate threat has passed. When you're injured, they may help modulate pain signaling to prevent excessive pain. When you're learning something new, they help regulate synaptic plasticity, the process by which neural connections strengthen or weaken. This modulatory role means the endocannabinoid system isn't usually driving processes on its own, but rather adjusting and fine-tuning processes driven by other systems. It's a supporting player, but an important one. The ECS often works like a fine-tuning system, helping the body maintain balance, sometimes called homeostasis. Homeostasis is the tendency of biological systems to maintain stable internal conditions despite external changes. Body temperature is maintained around 98.6 degrees Fahrenheit, even when the outside temperature varies. Blood glucose is kept within a narrow range even though food intake is intermittent. Blood pressure, pH, ion concentrations, all are regulated. The endocannabinoid system participates in these regulatory networks, often by providing feedback that dampens excessive responses. If a system is overactivated, endocannabinoids might help dial it back. If it's underactivated, reduced endocannabinoid signaling might allow more activity. This kind of feedback regulation is ubiquitous in biology, and the endocannabinoid system is one of many mechanisms the body uses to achieve it. Recognizing this can help frame cannabis use in a biological context. Plant cannabinoids are interacting with a system that's already there, adjusting its activity in ways that can be therapeutic, recreational, or problematic depending on the circumstances. It can be calming to know the body already has many quiet balancing systems running in the background, like invisible night shift caretakers. Your body is, at every moment, performing an enormous number of regulatory tasks without any conscious input from you. Your breathing adjusts to CO2 levels, your pupils dilate and constrict with light, your heart rate responds to activity, your immune system patrols for pathogens, your digestive system processes food, your kidneys filter blood, your liver metabolizes toxins. The endocannabinoid system is part of this silent, ongoing maintenance work. It's not something you can feel operating, not something you control voluntarily, but it's there, contributing to the overall stability and responsiveness of your body. When you consume cannabis, you're temporarily altering the activity of this system, adding signals that wouldn't normally be there, or blocking signals that would. Understanding that can change how you think about cannabis effects. They're not arbitrary or magical, but the result of specific biochemical interactions with an existing physiological system. With the body's signaling network gently outlined, we can talk about how scientists study cannabis, effects, especially how timing and delivery can change what researchers observe. Cannabis products can be delivered in different forms, which can change onset and duration of effects. This is pharmacokinetics, the study of how drugs are absorbed, distributed, metabolized, and excreted. The same active compound can behave very differently in the body depending on how it's administered. Injection is fastest, delivering the drug directly into the bloodstream. Inhalation is nearly as fast, as the lungs provide a large surface area for absorption and rapid access to circulation. Oral administration is slower because the drug must survive the acidic environment of the stomach, be absorbed through the intestinal wall, and pass through the liver before reaching general circulation. Topical application is slowest and most localized. Cannabis can be administered by all these routes, and each produces a different pharmacokinetic profile. Inhaled forms tend to have a faster onset because compounds enter the bloodstream through the lungs. When cannabis is smoked or vaporized, cannabinoids and terpenes enter the respiratory tract, diffuse across the thin membranes lining the alveoli, and enter pulmonary capillaries. From there, they travel directly to the heart and then to the brain, a journey that takes just a few seconds. Users typically feel effects within minutes, peak within 30 minutes to an hour, and return to baseline within a few hours. This rapid onset and offset makes it easier to titrate, to adjust the dose in real time based on effects, which is one reason inhalation has been historically popular. The downside is that inhaling combustion products, whether from cannabis or tobacco, exposes the lungs to tar and other potentially harmful substances, which is why vaporization, which heats cannabis without burning it, is often considered a safer alternative. Oral forms tend to have a slower onset because compounds pass through digestion and the liver first. When cannabis is ingested, in an edible, a capsule, or a tincture swallowed rather than held under the tongue, the cannabinoids must survive the stomach and be absorbed in the intestines. From there, they enter the hepatic portal circulation and pass through the liver, where enzymes metabolize them before they reach the general circulation. This first-pass metabolism delays the onset of effects, which can take anywhere from 30 minutes to 2 hours or more, and it also changes the chemical composition. THC, for instance, is partly converted to 11-hydroxy-THC in the liver, a metabolite that's actually more potent and longer-lasting than THC itself. The result is a different subjective experience, often described as more intense, more body-focused and longer-lasting than the inhaled THC, and a much longer duration, sometimes 6 to 8 hours or more. Because of this, research often separates inhaled and oral effects in study design. A clinical trial testing inhaled cannabis will use different protocols, different dosing schedules, and different outcome measures than a trial testing oral cannabis. The pharmacokinetics are so different that comparing results across routes of administration can be misleading without careful attention to these differences. Some effects might be more pronounced with inhalation, others with oral ingestion. Bioavailability, the fraction of the administered dose that reaches systemic circulation, also differs. Inhalation typically has higher bioavailability than oral ingestion, meaning a smaller inhaled dose might produce similar blood levels to a larger oral dose. These are the kinds of details that matter in rigorous research, and they highlight why generalizations about cannabis effects need to be qualified by specifying how the cannabis was administered. Edible products can be harder to study consistently because absorption varies with meals and metabolism. If you eat a cannabis edible on an empty stomach, absorption might be faster and more complete than if you eat it after a big meal. The presence of dietary fats can enhance cannabinoid absorption, since cannabinoids are lipid-soluble. Individual differences in gastrointestinal transit time, liver enzyme activity, and gut microbiome composition can all influence how much cannabinoid reaches the bloodstream and how quickly. This variability makes it challenging to predict effects from dose, which is a practical problem for users. What works one time might not work the same way the next, and a methodological problem for researchers who need consistent exposure to draw reliable conclusions. Some newer oral formulations attempt to address this by using encapsulation technologies or nanoemulsions designed to improve consistency, but traditional edibles remain quite variable. THC can be transformed into different metabolites in the body, especially after oral ingestion. The main metabolite, 11-hydroxy-THC, is formed by liver enzymes and can cross the blood-brain barrier. It's thought to contribute significantly to the effects of oral THC, and some users report that the edible experience feels qualitatively different from the inhaled experience in ways that might be explained by this metabolite. There are also inactive metabolites like THC-COH, which is what most workplace drug tests actually detect. These metabolites can persist in the body much longer than THC itself, stored in fat tissue and slowly released, which is why someone can test positive for cannabis use weeks after their last use, long after any intoxicating effects have worn off. Understanding metabolism is important for interpreting drug tests, for understanding duration of effects, and for developing new cannabinoid-based medications with desired pharmacokinetic properties. The same labelled amount does not always produce the same felt experience across different people. This is true for many drugs, but it's especially striking with cannabis. Two people can take the same edible, containing the same measured amount of THC, and have completely different experiences. One might feel pleasantly relaxed, the other anxious and overwhelmed. One might feel effects for 3 hours, the other for 7. This individual variation arises from differences in body weight, metabolism, tolerance, genetics, and psychological factors like mood and expectation. It's a reminder that dosing cannabis isn't as straightforward as dosing, say, aspirin, where the relationship between dose and effect is more predictable. In medical contexts, this means careful titration, Starting with a low dose and gradually increasing until the desired effect is achieved is usually necessary. In recreational contexts, it means caution is warranted, especially with edibles, where the delayed onset can tempt people to take more before the first dose has fully kicked in. Scientists try to control variables like dose, timing, and participant history to get clearer results. In a well-designed clinical trial, researchers will specify exact cannabinoid content, use standardized preparations, administer doses at specific times, and select participants with similar characteristics or stratify them by relevant variables like prior cannabis use. They'll use placebo controls, blinding procedures, and statistical methods to account for variability and detect real effects amid the noise. This is how science manages the complexity of individual variation, not by eliminating it, which is impossible, but by measuring it, controlling for it where possible, and using rigorous methods to separate signal from noise. The result is a growing body of evidence that, while far from complete, is much more reliable than anecdote or speculation. In medical contexts, standardized preparations are preferred because they are easier to measure and compare. A pharmaceutical-grade cannabinoid product will specify exact amounts of active ingredients, will have been tested for consistency, batch to batch, and will have known pharmacokinetic properties. This standardization makes it possible to determine optimal doses, predict effects, and identify side effects in a systematic way. Whole plant cannabis, especially when sourced from multiple growers or products, is harder to standardize. Cannabinoid and terpene profiles can vary, even within the same named variety, which complicates both clinical use and research. This tension between standardization and naturalistic use is a recurring theme in cannabis medicine. Standardized products allow for better science, but may not reflect how most people actually use cannabis, while whole plant products may be more representative but harder to study rigorously. A soothing thought is that biology is like ocean tides, the same moon but different shorelines. The moon pulls on the Earth's water with gravitational force, creating tides that rise and fall in a predictable rhythm. But the specific height and timing of the tide varies, depending on the coastline, the shape of the seafloor, the presence of bays and inlets, and local weather. The same fundamental force produces different local effects. Similarly, a cannabinoid like THC exerts its effects through a consistent mechanism, binding to CB1 receptors, but the outcome for any individual depends on their unique biology, psychology, and circumstances. There's both universality and individuality in how drugs work, and recognizing both can help us hold complexity without frustration. We can understand the general principles while accepting that details will vary, and that variation is not a failure of understanding, but a feature of biological reality. Now we'll drift into the careful world of medical research, what has been studied, what is clearer, and what still remains uncertain. Researchers have studied cannabis and cannabinoids for pain, nausea, appetite, sleep, seizures, and other areas. The breadth of this research reflects both the complexity of the endocannabinoid system, which touches many physiological processes, and the long history of cannabis use for various ailments. Some of these applications have ancient or traditional roots, others are more recent hypotheses based on cannabinoid pharmacology. The quality and quantity of research varies widely by indication. Some areas, like chemotherapy-induced nausea or certain epilepsy syndromes, have been studied in rigorous randomized controlled trials. Others, like fibromyalgia or PTSD, have less robust evidence, often only small studies or observational data, and some popular uses, like general wellness or stress relief, have little formal research support, existing mainly in the realm of anecdote and personal experience. Evidence can differ widely depending on the condition and the exact cannabinoid used. For nausea and appetite stimulation in the context of chemotherapy or HIV/AIDS, synthetic THC medications have shown benefit in controlled trials and have been approved for these indications. For certain rare epilepsies, pharmaceutical CBD has demonstrated clear efficacy. For chronic pain, the evidence is mixed. Some studies show modest benefit, others show no significant difference from placebo, and the size of the effect when present is often small. For anxiety and depression, preliminary results are intriguing but inconclusive. For sleep, many users report benefits, but controlled trials are limited and results are inconsistent. The picture that emerges is not one of a panacea, but of specific cannabinoids showing promise for specific conditions, with much more research needed to clarify where they're truly helpful and where they're not. Some prescription medicines are cannabinoid-based, developed with specific dosing and quality control. These medications represent the translation of cannabis science into formal medicine, with all the regulatory oversight, testing, and standardization that implies. They're not the same as medical cannabis programs, where patients obtain whole plant products from dispensaries. They're FDA-approved or similarly regulated drugs with specific indications, dosing guidelines, and monitoring requirements. The existence of these medications demonstrates that cannabinoids can meet the standards of modern medicine when studied appropriately, but it also highlights a gap. Many patients use cannabis in ways that aren't captured by these prescription products, and there's ongoing debate about how to bridge clinical research, regulatory frameworks, and patient access. Dronabinol and nabilone are examples of prescription cannabinoids used for certain nausea-related indications. Dronabinol is synthetic THC in a capsule, approved for nausea and vomiting associated with chemotherapy and for appetite stimulation in AIDS wasting syndrome. Nabilone is a synthetic cannabinoid similar to THC, also approved for chemotherapy-induced nausea. Both have been available since the 1980s, making them among the earliest cannabinoid medications. They work reasonably well for their approved uses, though they can cause side effects typical of THC, dizziness, sedation, dysphoria, and some patients find them less effective or less tolerable than inhaled cannabis. The existence of these drugs demonstrates that cannabinoid pharmacology can be harnessed for therapeutic purposes, but their limited adoption also shows that translating cannabis into mainstream medicine is not straightforward. Cannabidiol, Epidiolex, is an example of a prescription CBD medicine approved for certain seizure disorders. Epidiolex was approved in the United States in 2018 for Dravet syndrome and Lennox-Gastaut syndrome, two rare and severe forms of childhood epilepsy. The approval was based on rigorous clinical trials showing that CBD significantly reduced seizure frequency compared to placebo, and it marked a milestone in cannabinoid medicine, the first time a plant-derived cannabinoid, as opposed to synthetic, was approved as a pharmaceutical. Epidiolex is a purified CBD extract, standardized and tested for consistency, and it's administered as an oral solution with careful dosing based on body weight. Its success has spurred interest in CBD for other neurological conditions, but so far the evidence for other indications is much less strong. It's a reminder that evidence from one condition doesn't necessarily generalize to others, and that rigorous testing is needed for each potential use. Medical studies often focus on measured outcomes rather than personal anecdotes. This is a defining feature of scientific medicine. Rather than relying on stories about what helped someone, research asks, in a group of patients with a defined condition, does treatment with a specific cannabinoid lead to statistically significant improvement in predefined outcome measures compared to a control group? Those outcome measures might be seizure frequency, pain scores on a validated scale, quality of life questionnaires, sleep, diaries, or objective measurements like blood tests or imaging results. The goal is to produce data that can be aggregated, analysed, and replicated, building a body of evidence that is less subject to bias and placebo effects than individual testimonials. Anecdotes are valuable for generating hypotheses and understanding patient experiences, but they can't replace controlled trials for establishing efficacy. Sleep-related research is especially complex because sleep is influenced by stress, routine, light exposure, and many other factors. Cannabis is widely used for sleep, with many people reporting that it helps them fall asleep faster or stay asleep longer. Some research supports this, particularly for THC, which can reduce sleep onset latency and increase total sleep time. However, THC also appears to reduce REM sleep, the stage associated with dreaming, and the long-term consequences of chronic REM suppression are unclear. CBD's effects on sleep are even less certain, with some studies suggesting it might promote wakefulness at low doses and sedation at high doses. Moreover, tolerance to the sleep-promoting effects of cannabinoids can develop, and withdrawal from chronic use can produce rebound insomnia. Disentangling these effects from confounders like anxiety, pain, or sleep disorders that might be driving both cannabis use and sleep problems requires carefully designed studies, which are relatively rare. Scientists also study potential risks and side effects alongside potential benefits. This is good practice in all drug research. Every medication has a risk-benefit profile, and the goal is to understand both sides well enough to make informed decisions. For cannabinoids, the acute risks include impairment, anxiety, increased heart rate, and in rare cases, psychotic symptoms. The long-term risks of chronic use might include tolerance, dependence, respiratory issues from smoking, and possible cognitive effects, particularly with heavy use starting in adolescence. There are also drug interactions. CBD, for instance, inhibits certain liver enzymes and can affect the metabolism of other medications. Pregnancy and breastfeeding present additional concerns, as cannabinoids can cross the placenta and enter breast milk, with unknown consequences for fetal and infant development. Responsible research tries to characterize all of these risks as thoroughly as possible, not to discourage use categorically, but to enable informed decision-making. The strongest medical conclusions usually come from repeated studies, not a single headline. This is a key principle of evidence-based medicine. A single study, no matter how well designed, is just one data point. It might have flaws in its methods, unusual characteristics in its patient population, or results that occurred by chance. Replication, seeing whether other researchers, using similar methods with different patients, get similar results, is essential for building confidence. Meta-analyses and systematic reviews, which pool data from multiple studies, provide a higher level of evidence than individual trials. This is why scientists are often cautious in their claims, and why medical guidelines emphasize waiting for a body of evidence rather than acting on preliminary findings. It can be frustrating when a promising study doesn't immediately translate to clinical practice, but this conservatism protects patients from ineffective or harmful treatments that might look good in initial research but fail upon closer scrutiny. In calm science, uncertainty is not a failure. It's simply a label that says, we're still learning. There are many questions about cannabis and cannabinoids that remain open. Optimal doses for various conditions are often unknown. The relative importance of different cannabinoids and terpenes is debated. The mechanisms underlying certain effects are incompletely understood. Long-term outcomes of medical cannabis use in specific populations haven't been well studied. These gaps in knowledge are not shameful or surprising. They're normal in a relatively young field with complex subject matter. Science progresses incrementally, and uncertainty is part of the process. Acknowledging what we don't know, alongside what we do, is a mark of intellectual honesty. For someone trying to make decisions about cannabis use, it means accepting that perfect information isn't available, and that choices must be made with the best available evidence, updated as new information emerges. With research gently in view, we can also hold the other side of the story, common risks and trade-offs, without alarm, just clarity. THC can impair attention, coordination, and reaction time for a period after use. These effects are well documented and consistent across studies. They arise from THC's influence on brain regions involved in motor control, attention, and cognitive processing. The impairment is dose-dependent. Higher doses produce more impairment, and it's temporary, fading as THC is metabolized and eliminated from the body. For most people using moderate doses in a safe environment, this impairment is not dangerous, but it does create risks in certain contexts, particularly those requiring quick reactions, complex decision-making, or precise coordination. The impairment is comparable in some ways to that from alcohol, though the specifics differ. Alcohol tends to impair motor function more, while THC may impair attention and time perception more, and like alcohol, it makes activities like driving or operating machinery unsafe. Because of impairment, safety concerns often focus on driving and complex tasks. Epidemiological studies show that driving under the influence of cannabis increases the risk of accidents, though the magnitude of the increase is debated and appears smaller than for alcohol. Experimental studies using driving simulators show that THC impairs lane tracking, reaction time, and the ability to respond to unexpected events. Some users, particularly experienced ones, may partially compensate for impairment by driving more cautiously, but this doesn't eliminate the risk. Many jurisdictions have laws against driving with detectable THC levels or while impaired, and these laws reflect the public health concern that impaired driving poses risks not only to the user, but to others on the road. The same principle applies to any task where impairment could cause harm: operating machinery, caring for children, performing surgery, contexts where clarity and quick reactions matter. Some people experience unpleasant anxiety or paranoia with THC, especially at higher doses. This is one of the more common negative effects reported by users. It can range from mild nervousness to intense distressing panic. The mechanisms aren't fully understood, but likely involve THC's effects on the amygdala and other brain regions involved in fear and threat detection. Set and setting matter. Anxiety is more likely in unfamiliar or threatening environments, or when the user is already anxious. Dose matters too. Low doses might reduce anxiety, while high doses increase it, a biphasic effect seen with several drugs. Individual susceptibility varies, possibly related to genetic differences in cannabinoid receptors or prior experiences with cannabis. For some people, anxiety from THC is so unpleasant that it precludes further use. For others, it's rare or manageable. Knowing this risk allows people to start with low doses, choose comfortable settings, and have strategies, like CBD co-administration or simply waiting it out, to manage anxiety if it occurs. Regular use can lead to tolerance, meaning the same amount produces less effect over time. This is a well-established phenomenon with THC and probably occurs to some degree with other cannabinoids. The mechanisms involve downregulation of cannabinoid receptors. The body reduces the number or sensitivity of receptors in response to chronic stimulation, and possibly other adaptive changes in neural circuits. Tolerance can develop within days to weeks of regular use, and it's reversible with abstinence, as receptor levels gradually return to baseline. For medical users, tolerance can be problematic because it means increasing doses are needed to maintain therapeutic effects, which can increase side effects and costs. For recreational users, it can drive escalating use patterns. Some users manage tolerance by taking periodic breaks from cannabis, allowing receptors to recover, a practice sometimes called a tolerance break. Some people can develop cannabis use disorder, a pattern of use that becomes hard to control and causes problems. This is defined in diagnostic manuals as meeting certain criteria, using more or for longer than intended, unsuccessful efforts to cut down, spending a lot of time obtaining or using cannabis, craving, neglecting responsibilities, continuing use despite social or interpersonal problems, giving up activities, using in hazardous situations, continuing despite physical or psychological problems, tolerance, and withdrawal. Not everyone who uses cannabis will develop this disorder, most don't, but some will, particularly those who use frequently and heavily. The prevalence is estimated at around 9% of people who ever use cannabis, higher among those who start in adolescence or use daily. Cannabis use disorder is real and can be disruptive to people's lives, but it's less common and generally less severe than use disorders associated with substances like alcohol, opioids, or stimulants. Recognizing it as a possibility allows for awareness and, when needed, appropriate treatment, which often includes behavioral therapies. Adolescence is a sensitive period for brain development, which is why many public health guidelines emphasize caution for youth. The brain undergoes significant maturation during adolescence and early adulthood, particularly in the prefrontal cortex and in the pruning and strengthening of neural connections. Cannabis used during this period might interfere with these processes, though the evidence is complex and sometimes contradictory. Some longitudinal studies suggest associations between heavy adolescent cannabis use and outcomes like lower educational attainment, cognitive changes, and increased risk of mental health problems. However, establishing causation is difficult. Adolescents who use cannabis heavily may differ in other ways from those who don't, and disentangling cannabis effects from other confounders is challenging. Still, the precautionary principle suggests minimizing exposure during developmental periods, and most public health authorities recommend delaying cannabis use until adulthood. For some individuals, heavy THC exposure may be associated with higher risk of psychosis-like symptoms, especially in those with vulnerability. This is one of the more concerning potential risks. Psychosis involves a loss of contact with reality, including hallucinations, delusions, and disorganized thinking. Some studies, particularly from populations with high-potency cannabis use, have found associations between heavy cannabis use and increased risk of psychotic disorders like schizophrenia. The relationship appears to be dose-dependent and possibly influenced by genetic factors. People with certain genetic variants or family histories of psychosis may be more susceptible. Whether cannabis causes psychosis or simply triggers it in vulnerable individuals and whether it does so in people who would have developed psychosis anyway are debated. What seems clear is that for most people, even heavy use doesn't cause psychosis, but for a small subset, there may be real risk, and this is another reason for caution, particularly among adolescents and those with personal or family histories of mental illness. CBD can also have side effects and interactions, including with certain medications depending on dose and context. While CBD is often portrayed as safe and benign, it's not without risks. Common side effects in clinical trials include fatigue, diarrhea, and changes in appetite or weight. At the high doses used for epilepsy, sometimes several hundred milligrams per day, liver enzyme elevations have been observed, requiring monitoring. CBD inhibits cytochrome P450 enzymes in the liver, which are responsible for metabolizing many medications. This means CBD can increase blood levels of drugs like warfarin, clobazam, and others, potentially causing toxicity or requiring dose adjustments. This interaction risk is relevant for anyone taking multiple medications and considering adding CBD, and it highlights the importance of medical supervision. CBD is likely safer than THC in many respects. It doesn't impair driving, doesn't cause intoxication, and appears to have lower abuse potential, but safer doesn't mean completely safe. India's medicine, natural, does not automatically mean risk-free, just as synthetic does not automatically mean dangerous. This is worth emphasizing because there's a tendency in popular culture to equate natural with good and synthetic with bad. But nature produces many toxins: arsenic, mercury, poisonous mushrooms, snake venom, and laboratories produce many safe and effective medicines: insulin, antibiotics, vaccines. Cannabis is natural, but it still has risks. Synthetic cannabinoids created in labs can be more dangerous than plant-derived ones, particularly certain illicit designer cannabinoids. But pharmaceutical synthetic cannabinoids like dronabinol are well characterized and relatively safe when used as directed. The relevant question is not whether something is natural or synthetic, but what its specific effects and risks are, based on evidence. The calm approach is to treat cannabis like any bioactive substance, something to understand with respect, not fear. Fear is not a helpful lens for understanding drugs, but neither is uncritical enthusiasm. Cannabis, like coffee, alcohol, aspirin, or any other psychoactive substance humans use, has benefits and risks, effects and side effects, appropriate and inappropriate uses. The task is to understand these as clearly as possible, based on the best available evidence, and to make informed decisions in light of personal values, circumstances, and goals. Respect means taking the substance seriously, recognizing that it has real effects on the body and brain, without catastrophizing or moralizing. It means staying curious, critical, and open to updating views as new information emerges. And it means recognizing that different people will make different choices based on their own situations, and that's okay. Now we'll widen out to culture and law, the way cannabis has been labelled, regulated and debated across different places and times. Cannabis laws vary widely across countries, states and regions. In some places, possession of any amount is a serious criminal offence. In others, cultivation and sale are legal and regulated like alcohol or tobacco. In still others, there's a patchwork of medical permissions, decriminalisation, and grey markets. This variability reflects different cultural attitudes, different political priorities, different histories with the plant, and different assessments of the risks and benefits of prohibition versus regulation. The fact that laws can be so different for the same plant highlights that legal status is a social and political construct, not an inherent property of the substance itself. What's legal or illegal depends on where and when you are, and those boundaries can shift. Legal categories can change over time as policies and public attitudes shift. In recent decades, many jurisdictions have moved toward less punitive approaches, driven by changing public opinion, recognition of the harms caused by criminalisation, and interest in potential medical benefits. Some places have decriminalised personal possession, treating it as a civil infraction rather than a crime. Others have legalised medical use, creating systems for patients to access cannabis with physician recommendations. Still others have legalised recreational use for adults, establishing regulated markets with licenses, taxes, and quality controls. These changes don't happen uniformly or predictably. Some regions liberalise while others maintain strict prohibitions, and they're shaped by political processes, advocacy, research, and cultural conversations. The trajectory in many places seems to be toward greater acceptance and legal access, but this is not universal, and there are also instances of policy reversals or new restrictions. Cannabis has a long history that includes traditional uses, prohibitions, medical research, and modern industries. Archaeological evidence suggests humans have used cannabis for thousands of years, possibly as long as 10,000 years. It's been used for fibre in textiles and rope, for seeds as food, and for its psychoactive and medicinal properties. Different cultures have integrated it into religious rituals, medical systems, and recreational practices. In the 20th century, many countries, influenced by international treaties and domestic politics, criminalized cannabis, creating a period of prohibition that shaped law enforcement, criminal justice, and popular perceptions. In recent decades, the pendulum has swung back in many places, with renewed medical research, emerging legal markets, and evolving cultural narratives. This long arc, from ancient use through prohibition to contemporary re-evaluation, is a complex story involving colonialism, racism, economic interests, medical science, and social movements. Language around cannabis can carry cultural and political meanings, which is why terms differ across communities. Marijuana versus cannabis, weed versus medicine, getting high versus feeling relief. These aren't just synonyms with different sounds. They carry different connotations and reflect different perspectives. Some terms have been associated with stigmatization and criminalization, others with legitimacy and healing. Some communities prefer certain terms because of their cultural history, others avoid those same terms for the same reason. Being aware of this linguistic landscape can help in communicating clearly and respectfully. It's also a reminder that conversations about cannabis are never purely scientific or medical. They're always embedded in social contexts that shape how the plant is understood and discussed. Marketing terms like sativa and indica are common, but chemical profiles can be more informative than labels. In dispensaries and cannabis culture, products are often labelled as sativa, indica, or hybrid, with claims that sativas are energizing and indicas are sedating. These labels have some historical basis in plant, morphology, and geography, but modern genetic analysis shows that most cannabis plants are hybrids, and that the sativa/indica distinction doesn't reliably predict effects. What matters more is the specific cannabinoid and terpene content. A so-called indica high in limonene and low in myrcene might feel quite different from one with the opposite profile, even if both are labelled indica. Lab testing that provides cannabinoid and terpene percentages is a more reliable guide to predicting effects than traditional variety names. This shift from folk taxonomy to chemical characterization is part of cannabis becoming more like other commodities, where quality and characteristics are defined by measurable properties. Modern testing can measure THC, CBD, and terpene profiles to describe products more precisely. Labs use chromatography and mass spectrometry to separate and quantify dozens of compounds in a sample. A certificate of analysis will list major cannabinoids: THC, THCA, CBD, CBDA, CBG, CBN, as well as terpenes like myrcene, limonene, pinene, linalool, and caryophyllene. It may also test for contaminants like pesticides, heavy metals, molds, and residual solvents, providing a comprehensive snapshot of product quality and safety. This kind of testing is required by law in many regulated markets, and it represents a significant advancement over the days when users had no reliable information about what they were consuming. It also enables research. Studies can use products with defined chemical compositions, making results more interpretable and replicable. Over time, testing data may also reveal patterns linking specific chemical profiles to specific effects, though that work is still in its early stages. In public health, conversations often focus on harm reduction, accurate labelling, and preventing youth access. Harm reduction is a pragmatic approach that accepts that some people will use substances and seeks to minimize the harms associated with that use, rather than insisting on abstinence. For cannabis, harm reduction might include encouraging vaporization over smoking to reduce respiratory harm, providing clear dosing information to prevent overconsumption, or offering education about the risks of driving while impaired. Accurate labeling, ensuring products contain what they claim and are free of contaminants, protects consumers and builds trust in legal markets. Preventing youth access is a priority in most regulatory schemes, based on the concern that adolescent use might carry greater risks than adult use. These public health goals can sometimes be in tension with other objectives like maximising tax revenue or maintaining strict controls, and finding the right balance is an ongoing policy challenge. In science, the most trusted knowledge tends to be slow knowledge, careful, measured, and repeatable. This is worth holding on to as a general principle. Quick headlines, preliminary findings, and single studies can be exciting, but they're often overturned or qualified by subsequent work. The knowledge that lasts, that becomes part of the established scientific consensus, is built slowly through accumulation of evidence, replication, peer review, and critical evaluation. It's less flashy, but more reliable. For cannabis, where there's been a surge of research interest in recent years, this means being patient and critical, not accepting every new study as definitive, but watching for patterns that emerge across multiple studies and research groups. The science will continue to evolve, questions will be answered and new ones will arise, and our understanding will deepen incrementally. That's how science works, and there's something calming about trusting that process. Tonight, you don't need to resolve the debates or memorize the chemistry. The purpose of this long, gentle exploration has not been to turn you into an expert or to convince you of a particular position on cannabis. It's been to offer information in a calm, unhurried way, letting facts settle without pressure. Cannabis is a complex topic, botanically, chemically, medically, legally, culturally, and no single sitting, no matter how long, can capture every nuance. But you've encountered many pieces: the plant itself with its leaves and trichomes and life cycle, the cannabinoids with their different structures and effects, the terpenes that shape aroma, the endocannabinoid system that exists in your body, the ways science studies effects and tries to separate signal from noise, the medical research that's been done and the uncertainties that remain, the risks and trade-offs, the cultural and legal contexts that shape how the plant is understood and used. These pieces form a mosaic, incomplete perhaps, but coherent enough to provide a sense of the whole. You can simply let the topic rest on a shelf, like a quiet museum display, while you return to your steady breath and drift towards sleep. Imagine setting this information aside, gently closing the mental file, stepping away from the exhibit. The facts will still be there if you want to return to them, but for now they can simply exist in the background, inert and undemanding. Your mind can release the effort of holding on to details, the work of evaluating claims, the complexity of weighing evidence. In their place, you can feel the simple physical presence of your body, the weight of your head on the pillow, the softness of the blanket, the rise and fall of your chest with each breath. The complicated world of molecules and receptors and policies recedes, and what remains is the immediate, uncomplicated reality of this moment. You, breathing, resting, safe. Take a slow inhale, and then a longer exhale, and let the busy world of labels and opinions soften into silence, leaving only calm, easy rest. Feel the air move in, cool and smooth, filling your lungs, and then feel it release, warm and slow, carrying with it any remaining tension or mental effort. Each breath is complete in itself, nothing to remember, nothing to decide, just the ancient rhythm of breath moving through you. The cannabis plant, with all its chemistry and history, continues its existence somewhere out in the world, growing in fields or greenhouses, being studied in laboratories, being used by people for myriad reasons. But here, now, in this quiet space, none of that requires your attention. You've learned what you've learned, and it's enough. There's nothing more to do, nowhere else to be, nothing to hold on to. Just breath and warmth and the gentle pull of sleep welcoming you in. The next story is about to begin. Please relax and enjoy. Mushrooms are the fruiting bodies of certain fungi, and understanding what that means can help us appreciate these quiet organisms in a new way. When we see a mushroom growing on a forest floor or emerging from the side of a rotting log, we're looking at just one small part of a much larger living thing. The mushroom itself, the cap, the stem, the visible structure, is really just the reproductive organ of the fungus, appearing above ground or above the surface of wood when conditions are right for spreading spores. The rest of the organism, the main body of the fungus, is usually hidden from view, living beneath the soil or inside the wood where it quietly grows and feeds. Fungi belong to their own kingdom of life, separate from both plants and animals. For a long time, people grouped fungi with plants because mushrooms seem to grow from the ground like flowers or vegetables. But fungi are fundamentally different from plants in several important ways. Plants use photosynthesis to create their own food from sunlight, carbon dioxide, and water. They're producers, making energy from light. Fungi, on the other hand, cannot photosynthesize. They have no chlorophyll, no green pigment to capture sunlight. Instead, fungi are more like animals in how they obtain nutrition. They consume organic matter, breaking down food sources in their environment and absorbing the nutrients they need. This makes them heterotrophs, organisms that rely on other organisms or organic material for sustenance. But fungi accomplish this feeding in their own unique way, different from how animals eat and digest. They release enzymes into their surroundings, breaking down complex molecules outside their bodies, then absorbing the simpler compounds that result. This external digestion is one of the defining characteristics of fungi. The mushroom we see is often just the visible part of a much larger organism hidden in soil or wood. Think of it like an iceberg, where the small portion above, water, represents the mushroom, and the massive structure below represents the main body of the fungus. This hidden body is what does most of the work, absorbing nutrients, growing, surviving through seasons, and maintaining the life of the organism. The mushroom appears only when the fungus is ready to reproduce, emerging to release spores and then often withering away fairly quickly. Some mushrooms last just a few days, while others might persist for a week or two, but many are temporary structures compared to the longer-lived organism beneath. Many fungi grow as thin threads called hyphae, and these microscopic filaments are the basic building blocks of fungal structure. If you could shrink down and observe a single hypha under high magnification, you'd see a tubular cell, often just a few micrometers in diameter, with a wall made of chitin, the same material that forms insect exoskeletons and crab shells. Hyphae grow at their tips, extending forward into new territory, branching, and exploring their environment. They're surprisingly strong for their size, able to penetrate dense materials and push through soil particles. As a hypha grows, it can branch, creating new tips that spread in different directions. Some hyphae have cross walls dividing them into cellular compartments, while others form long tubes with multiple nuclei and no dividing walls. This growth pattern allows fungi to explore their surroundings efficiently, reaching toward food sources and avoiding areas that don't provide nutrition. A network of hyphae is called mycelium, and this collective structure is where the real life of the fungus happens. Mycelium can be thought of as the fungus itself, the living organism that persists year after year. When hyphae branch and interconnect, they form a dense, web-like network that can extend through soil, leaf litter, rotting wood, or any organic material the fungus feeds upon. Individual hyphae are microscopic, but together millions of these threads create a structure that can be surprisingly large. Some mycelia spread across just a few cubic inches of soil, while others extend across many square feet or even acres. The mycelium is constantly growing, dying back in places where resources are exhausted and extending into new areas where food is available. It's a dynamic system, responding to its environment with a kind of simple intelligence, growing toward nutrients, avoiding toxic substances, and adjusting to changes in moisture and temperature. Mycelium can spread through soil like fine lace or soft webbing, creating an intricate underground network. If you were to carefully sift through a handful of healthy forest soil, you might notice fine white threads running through the dark earth. These are hyphae, parts of various fungal networks threading through the spaces between soil particles. The mycelium doesn't grow in a random tangle. It tends to form organized patterns, radiating outward from a central point or spreading along favorable paths where moisture and nutrients are abundant. In some cases, mycelium forms fairy rings, circular patterns where mushrooms emerge in a ring-like formation, the result of mycelium spreading outward evenly in all directions from a central starting point. As the mycelium at the center exhausts local food sources, the growing edge continues expanding outward, and mushrooms appear at this active frontier. These rings can expand slowly over many years, some growing just a few inches per year, while the mycelium behind the fruiting edge quietly works on decomposition. Mushrooms appear when a fungus is ready to reproduce, triggered by environmental conditions that signal the right time for spore release. temperature, moisture, and sometimes the changing length of days can all influence when a fungus decides to produce mushrooms. Many mushrooms emerge after rain, when the soil is saturated and the air is humid, conditions that help keep the delicate fruiting body from drying out and that create favourable circumstances for spore dispersal. Some fungi fruit in spring, others in summer, and many wait for autumn when temperatures cool and rainfall increases. The timing is often species-specific, with certain mushrooms reliably appearing at the same time each year if conditions allow. When the mycelium senses that conditions are favourable, it begins to redirect resources and energy toward producing a fruiting body. Hyphae aggregate and organise themselves into the structure that will become the mushroom, forming the stem, the cap, and the spore-producing tissues in an impressively coordinated process. The main purpose of many mushrooms is to release spores, those tiny reproductive cells that will disperse and potentially start new fungal colonies elsewhere. Everything about a mushroom structure is designed to maximise spore production and dispersal. The cap protects the spore-producing surfaces beneath it from rain that might wash spores away prematurely. The stem lifts the cap up into air currents that can carry spores away from the parent mushroom. The gills, pores, or other structures on the cap's underside create enormous surface area where millions or billions of spores can be produced. A single mushroom can produce staggering numbers of spores. Some estimates suggest that a large mushroom might release trillions of spores over its lifetime. Most of these spores will never successfully establish a new fungus. They'll land in unsuitable locations, dry out, get eaten by tiny organisms, or simply fail to find the conditions they need to germinate. But by producing such enormous numbers, fungi ensure that at least some spores will survive and continue the species. Spores are tiny reproductive cells that can travel through air or water, serving as the fungus's way of reaching new locations. These microscopic structures are incredibly small, typically just a few micrometers across, small enough to remain suspended in air, currents for long periods. Spores are often protected by tough cell walls that help them survive harsh conditions. Some can endure freezing temperatures, intense heat, desiccation, and UV radiation, remaining dormant but viable until they land in a place where germination is possible. The shape, colour, and surface texture of spores vary tremendously between species, and mycologists often use these characteristics to help identify fungi. Some spores are smooth and round, others are elongated or ornamented with spines and ridges. Some are colourless, while others are pigmented in shades of brown, black, pink, or even purple. When millions of spores are released together, they can create a visible spore print, a deposit of coloured powder on any surface beneath the mushroom, useful for identification and also a beautiful reminder of the fungus's reproductive effort. A calm way to imagine a mushroom is as a forest's quiet flower, blooming briefly for spores. Like flowers, mushrooms can be beautiful, displaying diverse colours, shapes and textures. Like flowers, they're ephemeral, appearing for a short time and then fading. And like flowers, their purpose is fundamentally about reproduction, about creating and dispersing the next generation. But unlike flowers, which rely on bright colours and sweet scents to attract pollinators, mushrooms often work more passively, relying on wind, rain splash, or gravity to move their spores. Some mushrooms do attract animals, producing odours that draw insects or releasing spores that animals will carry away on their bodies or in their digestive tracts. But many mushrooms simply stand quietly, releasing spores into the air and trusting the wind to carry them. There's something peaceful about this strategy. No urgency, no competition for pollinators, just a patient release of reproductive cells into the environment, day after day, until the mushroom withers and collapses. Now that mushrooms feel familiar, we can drift beneath the surface to meet the real everyday worker, the hidden mycelium. While mushrooms capture our attention with their visible presence, the mycelium is where the continuous work of the fungus occurs. It's the mycelium that absorbs nutrients, that grows and maintains the organism through seasons and years, that responds to environmental changes and that ultimately produces the mushrooms we see. Understanding mycelium helps us appreciate that fungi are not just the mushrooms that appear occasionally, but are persistent organisms that inhabit and shape their environments constantly. Mycelium is the main body of many fungi, the living network that persists even when no mushrooms are visible. In some ways, it's easier to understand fungi if we think of them as being like trees, where the mycelium is the trunk, branches and roots, the permanent structure, And the mushrooms are like flowers or fruit, seasonal additions that appear when conditions are right. The mycelium must gather enough energy and resources to maintain itself and to produce mushrooms when the time comes. This means that the mycelium is always working, always absorbing nutrients from its surroundings, always growing into new territory or maintaining its established network. Even in winter, where no mushrooms are visible and growth may slow or stop, the mycelium is often still alive beneath the soil or inside wood, dormant but ready to resume activity when temperatures warm and moisture returns. It can grow through soil, leaf litter, rotting logs, and even inside living roots, demonstrating remarkable versatility in where and how it lives. Soil is one of the most common habitats for mycelium, where fungal networks thread through the spaces between mineral particles and organic matter, absorbing nutrients from decomposing materials and forming relationships with plant roots. Leaf litter, the layer of fallen leaves that accumulates on forest floors, is another rich habitat full of carbon and nutrients, locked up in dead plant tissue. Mycelium can penetrate these leaves, releasing enzymes that break down cellulose and lignin, gradually reducing whole leaves to crumbly fragments. Rotting logs are particularly important habitats for many fungi. A fallen tree trunk is a massive reservoir of nutrients, and various fungal species will colonize it in succession over the years or decades it takes for the log to fully decompose. Some fungi specialize in attacking freshly fallen wood, while others prefer wood that's already partially decayed. Inside living roots, certain fungi form intimate partnerships, their hyphae actually entering root cells or forming dense sheaths around root tips, engaging in exchanges of nutrients that benefit both the fungus and the plant. Mycelium absorbs nutrients from its surroundings rather than making food from sunlight, and this fundamental difference from plants shapes everything about how fungi live. Without the ability to photosynthesize, fungi must find organic matter to consume. This makes them dependent on other organisms, either on the dead remains of plants and animals, or on living partnerships with organisms that can photosynthesize. The absorption process is efficient, but requires that the fungus be in direct contact with its food source. Hyphae grow toward nutrients, and once they reach an area rich in food, they proliferate, creating dense networks in nutrient-rich zones. The entire surface of the hyphal network can absorb nutrients, making the mycelium extremely effective at extracting resources from its environment. As nutrients are absorbed, they're transported through the hyphae to other parts of the mycelium, including to developing mushrooms when they're being produced. This transport happens through the movement of cytoplasm, the fluid contents of the fungal cells, which can flow through the hyphae in organized currents. Fungi release enzymes that break down complex materials into smaller pieces, performing their digestion outside their bodies before absorption. This is one of the most remarkable aspects of fungal biology. The enzymes that fungi produce are incredibly varied and powerful, capable of breaking chemical bonds that many other organisms cannot attack. For example, cellulose enzymes break down cellulose, the structural carbohydrate that makes up much of plant cell walls. Ligninase enzymes attack lignin, the tough, complex polymer that gives wood its strength and resistance to decay. Proteases break down proteins into amino acids. Lipases split fats into simpler components. By secreting these enzymes into dead wood, leaf litter, or soil, fungi essentially pre-digest their food in their environment, then absorb the simpler molecules that result. This external digestion means that fungi can tackle food sources that would be impossible for many other organisms to use. Dead wood, for instance, is nutritious, but locked away inside tough lignocellulose structures. Without fungi and bacteria to break it down, dead wood would persist almost indefinitely in many environments. Those smaller pieces can then be absorbed through the hyphae, completing the feeding process. Once enzymes have broken down large molecules into smaller ones, sugars from cellulose and starch, amino acids from proteins, fatty acids from lipids, these smaller molecules can pass through the cell walls and membranes of the hyphae. Fungi use active transport and other cellular mechanisms to move these nutrients into their cells, where they can be used for energy and growth. The efficiency of this process is remarkable. Fungi can extract nutrients from materials that seem completely used up, gleaning nutrition from sources that other organisms have already exploited. This scavenging ability makes fungi essential to ecosystem nutrient cycling, ensuring that elements like carbon, nitrogen, and phosphorus don't remain locked up in dead organic matter but instead return to forms that can be used by plants and other organisms, mycelium can be very large, spreading over wide areas when conditions are right. In fact, some of the largest organisms on Earth are fungi, their mycelia extending across enormous areas. One famous example is a honey fungus, Armillaria orstoii, in Oregon's Blue Mountains, where genetic testing revealed that a single individual mycelial network extends across more than 2,000 acres, making it one of the largest and oldest organisms known, estimated to be thousands of years old. Most mycelia are much smaller than this record holder, but even modest fungal colonies can be surprisingly extensive. A mycelium the size of a dinner plate might contain miles of hyphae when all the threads are added together. This extensive growth allows fungi to access resources across a broad area, connecting different patches of nutrients and transferring resources within their network. The mycelium can respond to local conditions, growing more densely where food is abundant and extending exploratory hyphae into new areas where nutrients might be found. Because it's hidden, a forest can contain far more fungus than we can see. When you walk through a forest, the visible mushrooms represent just a tiny fraction of the fungal biomass present. Most of the fungal life is invisible, woven through the soil and wood all around. Studies that have analysed forest soil have found astounding amounts of fungal tissue. In some temperate forests, the mass of fungal hyphae in the soil can exceed the mass of all the tree roots. In a single teaspoon of healthy soil, there might be miles of fungal hyphae threading through the particles and pore spaces. This hidden abundance underscores how important fungi are to forest ecosystems. They're not occasional visitors or minor players. They're fundamental, constant presences that shape soil chemistry, influence plant health, and drive the recycling of nutrients throughout the ecosystem. Mycelium often grows slowly and steadily, responding to moisture and food sources with patient persistence. While some fungi can grow quite rapidly under ideal conditions, you might notice a new patch of mycelium appearing on a log or spreading across compost within days. Most growth in natural environments is more measured. Hyphae extend at their tips, adding length bit by bit, hour by hour. The rate of growth depends on temperature, moisture, and the availability of food. Warm, moist conditions with abundant nutrients allow faster growth. Cold, dry, or nutrient-poor conditions slow growth considerably. Unlike animals that move to find food, mycelium stays put and grows toward resources. If you could watch a time-lapse of mycelium exploring a new substrate, you'd see hyphae extending and branching like slow-motion tendrils, searching for the best path forward, avoiding obstacles, and concentrating growth in the most rewarding areas. It can pause growth during dry times and continue when rain returns, showing a remarkable resilience. Fungi are well adapted to the variable conditions of many environments. When water is scarce, mycelium can become dormant, essentially waiting for better conditions. The hyphae might dry out and cease active growth, but they don't necessarily die. When rain returns and moisture penetrates the soil or wood where the mycelium lives, the fungus can rehydrate and resume growing, sometimes remarkably quickly. This ability to pause and resume activity allows fungi to persist through droughts, cold snaps, and other challenging periods. It also means that mushroom appearances can be unpredictable. After a long dry spell, a sudden heavy rain can trigger a flush of mushrooms as mycelia that have been waiting for moisture suddenly spring into reproductive mode. This pattern gives forests and grasslands their rhythms of fungal fruiting, periods of abundance alternating with times when few or no mushrooms are visible. Walking through a forest, you're often stepping over a quiet, living network. Every footfall lands on ground that's likely threaded with mycelium. The top few inches of soil, the decomposing leaf litter, the rotting logs, all are inhabited by fungi going about their slow work. This realization can change how you perceive a forest. It's not just the trees, ferns, birds, and insects. It's also this vast, mostly invisible community of fungi interconnected with the plant roots, breaking down the dead, feeding on the fallen, and creating the conditions that allow the visible forest to thrive. There's something humbling and comforting about this idea, that beneath the apparent stillness of the forest floor, there's constant activity at a microscopic scale, a biological engine quietly running, sustaining the ecosystem's cycles. With that underground calm in mind, let's explore fungi's gentle job as recyclers, turning old wood and leaves into fresh nutrients. Decomposition is one of the most essential ecological functions, and fungi are among the most important decomposers on the planet. Without decomposition, dead organic matter would accumulate endlessly, nutrients would be locked away in unusable forms, and ecosystems would grind to a halt. Fungi make it possible for death to transform into new life, completing the cycles that keep forests, grasslands, and other ecosystems healthy and productive. Many fungi are decomposers, meaning they break down dead organic material and return its components to the ecosystem. These decomposer fungi are sometimes called saprotrophs or saprophytes, terms that describe their lifestyle of feeding on dead matter. They're specialists at decay, equipped with enzymes that can dismantle the complex molecules in dead plants and animals. This is different from parasitic fungi, which feed on living hosts, and from symbiotic fungi, which form mutually beneficial partnerships. Decomposer fungi are recyclers, and their work is neither harmful nor helpful to individual organisms. It's simply essential to the ecosystem as a whole. They process leaves, wood, animal remains, and other organic debris, converting it into simpler substances that can re-enter the nutrient cycles that support new growth. Fallen leaves, dead trees, and old plant matter are all food sources for decomposer fungi. In autumn, temperate forests shed enormous quantities of leaves, creating a fresh blanket of organic matter on the forest floor. As these leaves lie on the ground, they become colonized by fungi and bacteria. Fungal spores land on the leaves, germinate, and send hyphae into the leaf tissue. Over weeks and months, the leaves gradually lose their structure, becoming softer, darker, and more fragmented. This is fungal decomposition in action. Dead trees, whether standing snags or fallen logs, provide a different kind of resource. Huge amounts of woody material that can take years or decades to fully decompose. Different fungi colonize wood at different stages. Some fungi attack recently dead trees, while others specialize in wood that's already partially rotted. The succession of fungal species on a decomposing log is a well-studied phenomenon, with certain mushrooms appearing only on fresh logs and others only on very rotten, crumbly wood. Fungi help return nutrients like carbon and nitrogen to the soil, making these elements available for uptake by plants and other organisms. Carbon, which plants fix from the atmosphere through photosynthesis, becomes incorporated into plant tissues, cellulose, lignin, proteins, and other compounds. When the plant dies, this carbon would remain locked in the dead tissue if not for decomposers. Fungi break down these carbon-containing molecules, respiring some of the carbon back into the atmosphere as carbon dioxide and incorporating some into their own bodies and into the soil as decaying organic matter. Nitrogen, a key nutrient that plants need but that's often in short supply, also gets locked up in dead plant and animal tissues. Fungal decomposition helps release nitrogen from proteins and other organic molecules, converting it into forms like ammonium that plants can absorb through their roots. This nitrogen cycling is crucial to maintaining soil fertility. Without decomposers, forests would pile up with undecomposed material, creating an ecosystem crisis. Imagine a forest where dead leaves never rotted, where fallen trees never decayed. Over time, the forest floor would become choked with layers and layers of intact dead plant material. Nutrients would become increasingly scarce in the soil because they'd all be tied up in this accumulating debris. New plant growth would slow and eventually cease for lack of available nutrients. Of course, this doesn't happen because decomposers, primarily fungi and bacteria, constantly work to break down dead material at roughly the same rate that it's produced. In healthy ecosystems, there's a balance between the input of dead organic matter and its decomposition. This balance maintains soil fertility and keeps ecosystems productive over the long term. Fungi can break down tough plant materials such as cellulose, the structural carbohydrate that makes up a large part of plant cell walls. Cellulose is made of glucose molecules linked together in long chains, and these chains are packed tightly together in plant tissues, making cellulose very stable and resistant to degradation. Most animals cannot digest cellulose directly. Even animals that eat plants, like cows and deer, rely on symbiotic bacteria and other microorganisms in their digestive systems to break down cellulose for them. Fungi, however, produce cellulose enzymes that can cleave the bonds between glucose molecules in cellulose, breaking the long chains into shorter segments and eventually into individual glucose molecules. This glucose can then be absorbed and used by the fungus for energy and growth. This ability to digest cellulose means that fungi can thrive on plant materials that many other organisms cannot use, giving them access to a huge reservoir of potential food in the form of dead leaves, grass, wood, and other plant debris. Some fungi can also break down lignin, a strong component of wood that's even tougher than cellulose. Lignin is a complex, irregular polymer that gives wood much of its strength and rigidity. It's also what makes wood resistant to decay. Lignin is so stable that it doesn't break down easily even under harsh conditions. Only certain fungi, notably white rot fungi and brown rot fungi, have evolved the enzymatic machinery to degrade lignin. White rot fungi can completely break down both lignin and cellulose, leaving behind pale, soft, spongy wood. Brown rot fungi primarily attack cellulose, leaving behind brown, crumbly wood that's rich in modified lignin. The ability to degrade lignin is ecologically crucial because it allows the vast amounts of carbon locked up in woody tissue to be recycled. Without lignin-degrading fungi, dead wood would persist almost indefinitely, and forests would be choked with ancient unrotted logs. This ability helps logs gradually soften and return to the earth, transforming wood into soil. A fallen tree trunk begins as solid, hard wood, but over years and decades fungal activity transforms it. The wood becomes softer, darker, and more porous. It begins to crumble when touched. Eventually it loses all structural integrity, collapsing into a pile of humus that enriches the soil. This transformation is not a violent or sudden process. It's slow, gentle, and thorough. As the log decays, it also becomes a habitat. Insects bore into the softening wood, birds excavate nests, small mammals find shelter in cavities, and plants send roots into the moist, nutrient-rich wood. A decomposing log supports a succession of life even as it breaks down, and by the time it's fully decayed, it has nurtured countless other organisms and contributed its stored nutrients back to the soil. Decomposition is usually slow, matching the quiet pace of forests. Unlike the rapid decomposition that occurs in hot, moist tropical environments or in compost heaps, forest decomposition in temperate and boreal regions is often measured in years. A leaf might take 1 to 3 years to fully decompose depending on its toughness and the local climate. A small branch might take 5 or 10 years. A large log might persist for 20, 50, or even more than 100 years before it's fully incorporated into the soil. This slow pace is partly due to temperature. Fungal and bacterial activity slows in cold conditions, and partly due to moisture availability. It's also a function of the toughness of the material being decomposed. Needles from pine trees, rich in resins and waxy coatings, decompose more slowly than leaves from deciduous trees. Hardwood logs, dense and full of lignin, take longer to decay than softer woods. Fungi often work alongside bacteria and small insects in recycling ecosystems, forming decomposer communities. Decomposition is rarely the work of a single organism. Instead, it's a collaborative effort involving many species. Bacteria are particularly important in breaking down soft, nitrogen-rich materials like animal carcasses and green plant tissue. Fungi excel at breaking down tougher, carbon-rich materials like wood and dry leaves. Together, bacteria and fungi complement each other's abilities, creating more complete and efficient decomposition than either group could achieve alone. Insects, mites, springtails, and other tiny invertebrates also play important roles. They physically fragment dead material, chewing leaves and wood into smaller pieces that have more surface area for microbial colonization. Some insects feed on fungi themselves, dispersing fungal spores and helping fungi colonize new substrates. This web of interactions means that decomposition is a community process, not just a fungal one, though fungi are often the key players. In a gentle way, fungi help forests tidy up without rushing. There's no urgency in decomposition, no deadline to meet. The forest produces dead material, leaves in autumn, branches after storms, trees at the end of their lifespans, and the decomposer community processes this material at its own pace. The pace is dictated by temperature, moisture, and the nature of the material itself. If conditions are cold or dry, decomposition slows. If it's warm and wet, it speeds up. But there's a balance, a rhythm that persists year after year. The forest doesn't accumulate endless debris, nor does everything disappear instantly. Instead, there's a layered structure to the forest floor, fresh leaves on top, partially decomposed material below, and fully humified organic matter mixed with mineral soil at the bottom. This structure reflects the progression of decomposition, with materials at different stages coexisting peacefully, each contributing to the forest's health in its own time. Now we can look at a calmer kind of partnership, when fungi don't just recycle, but cooperate with living plants and trees. Not all fungi are decomposers living on the dead. Many have evolved relationships with living plants, forming partnerships that are among the most important ecological relationships on Earth. These partnerships, called mycorrhizae, connect the lives of fungi and plants in ways that benefit both partners and shape entire ecosystems. Many fungi form partnerships with plant roots called mycorrhizae, a term that literally means fungus root. In these relationships, fungal hyphae associate closely with plant roots, sometimes forming a sheath around the outside of the root, sometimes penetrating between or even into root cells. These are not parasitic relationships where one partner benefits at the expense of the other. Instead, they're mutualistic, meaning both the fungus and the plant gain something valuable. The prevalence of mycorrhizae is remarkable. It's estimated that more than 90% of plant species form mycorrhizal associations. This means that when you look at a forest, a meadow, or even a garden, almost every plant you see is connected underground to a fungal partner. This partnership has deep evolutionary roots, likely dating back hundreds of millions of years to when plants first colonized land. Some scientists suggest that mycorrhizal fungi may have been essential to that colonization, helping early plants extract nutrients from barren mineral soils. In mycorrhizae, fungal threads connect with or enter a plant's roots, creating an intimate physical connection. There are several types of mycorrhizae, but the two most common are ectomycorrhizae and arbuscular mycorrhizae. In ectomycorrhizae, which are common in temperate forest trees like pines, oaks, and birches, the fungus forms a dense sheath of hyphae around the outside of fine root tips. Hyphae penetrate between root cells but don't usually enter the cells themselves. This creates a large interface between fungus and root where nutrients can be exchanged. In arbuscular mycorrhizae, which are common in grasses, crops, and many herbaceous plants, the fungus sends hyphae that penetrate the root and actually enter some of the root cells, forming highly branched structures called arbuscules inside the cells. These arbuscules are where the exchange of nutrients takes place, with the plant and fungus trading resources across the cell membrane. The fungus can help the plant absorb water and minerals from the soil, extending the plant's reach far beyond its own roots. Fungal hyphae are much finer than even the finest plant root hairs, allowing them to penetrate tiny soil pores that roots cannot access. The hyphae also extend much farther from the plant than roots typically do. A single plant's mycorrhizal network might extend through hundreds of cubic inches, or even cubic feet of soil, exploring far more area than the plant's roots could cover on their own. This extended reach is especially important for absorbing nutrients that don't move easily through soil, particularly phosphorus. Phosphorus is essential for plants. It's a key component of DNA, ATP, and other critical molecules, but it's often scarce in soil and doesn't diffuse readily through water. Mycorrhizal fungi can seek out phosphorus across a broad area and transport it back to the plant, making it available even when soil phosphorus levels are very low. The fungi also help with water absorption, gathering moisture from a larger volume of soil and helping the plant stay hydrated during dry periods. The plant can share sugars it made through photosynthesis with the fungus, providing the food energy that the fungus needs. This is the plant's side of the bargain. Because fungi cannot photosynthesize, they need a source of carbon-containing compounds to fuel their growth and metabolism. The plant, which is using sunlight to convert carbon dioxide and water into sugars, has an abundant supply of these compounds. In a mycorrhizal partnership, the plant transports some of its photosynthetically produced sugars, primarily glucose and other simple sugars, down to its roots and then transfers them to the fungus. The fungus uses these sugars for energy and to build more hyphae, which in turn gather more nutrients for the plant. In some forest ecosystems, it's estimated that plants may transfer 10% or more of the carbon they fix through photosynthesis to their mycorrhizal partners. That's a substantial investment, but one that pays off in improved nutrition and survival. This trade benefits both partners when conditions are right, creating a relationship of mutual support. The plant gets enhanced access to nutrients and water, which can improve its growth, health, and ability to survive stress like drought or nutrient deficiency. The fungus gets a steady supply of sugars and other carbon compounds, which it cannot make for itself. Both partners gain something they need, something they could not obtain as easily on their own. This kind of mutualism is common in nature, but mycorrhizae are particularly important because they're so widespread, and because they have such significant effects on plant performance and ecosystem function. In some cases, plants can grow without mycorrhizal partners, but they often grow more slowly and are more susceptible to stress. In other cases, certain plants are essentially dependent on mycorrhizae and will not thrive, or may not even survive, without their fungal partners. Mycorrhizal fungi can extend the effective reach of a plant's root system, sometimes dramatically so. Research has shown that the hyphal networks of mycorrhizal fungi can increase the absorptive surface area of a plant by hundreds or even thousands of times. If you were to measure all the surface area of a tree's roots and root hairs, and then add in all the surface area of the mycorrhizal hyphae connected to those roots, the total absorptive area would be vastly greater than the roots alone. This expanded network allows the plant to tap into nutrient and water reserves that would otherwise be inaccessible. It's like having an enormously extended root system without having to invest the energy and resources to grow all those roots. The plant gets the benefits of a much larger root system, but shares the cost with the fungus, which grows the hyphae and absorbs nutrients that benefit both partners. These partnerships are common in forests and grasslands, shaping the structure and function of these ecosystems. In forests, most trees form ectomycorrhizal or arbuscular mycorrhizal associations. The fungi involved are often species that produce the mushrooms we see on the forest floor: boletes, chanterelles, russulas, amanitas, and many others. These mushrooms are the fruiting bodies of the mycorrhizal fungi that live in partnership with tree roots. When you see a mushroom growing near a tree, there's a good chance it's connected, underground to that tree's roots, part of a mycorrhizal network. In grasslands, arbuscular mycorrhizae dominate, supporting the grasses and herbaceous plants that make up these ecosystems. The fungi involved in arbuscular mycorrhizae rarely produce large mushrooms. Their spores are usually distributed in soil or by animals, and the fungi themselves are mostly invisible, known primarily through microscopic examination of roots and soil. Different plant species often associate with specific types of mycorrhizal fungi, showing preferences or compatibility patterns. Some trees, like pines, primarily form partnerships with specific groups of ectomycorrhizal fungi. Other trees, like maples, form associations with different fungal groups. Some plants are generalists, forming partnerships with many different fungal species, while others are more selective. These preferences can influence forest composition and diversity. If a particular tree species needs a particular mycorrhizal fungus to thrive, the presence or absence of that fungus can determine whether the tree can successfully establish in a given area. In some cases, foresters have found that when planting trees in new areas, inoculating the soil with appropriate mycorrhizal fungi can greatly improve tree survival and growth. This practical application of mycorrhizal science demonstrates how important these partnerships are. This relationship can support healthier plant growth and better nutrient uptake, with measurable benefits. Studies comparing plants with and without mycorrhizal fungi consistently show that mycorrhizal plants tend to grow larger, produce more biomass, and have better access to nutrients, especially phosphorus and nitrogen. Mycorrhizal plants often show improved drought tolerance, possibly because the extensive hyphal network helps them access water during dry periods. Some research also suggests that mycorrhizal fungi can help protect plants from certain soil-borne diseases, either by outcompeting pathogenic organisms or by enhancing the plant's own defense mechanisms. These benefits can translate into better crop yields in agriculture, healthier trees in forests, and more resilient plant communities in natural ecosystems. The relationship is not always beneficial. Under some conditions, the cost to the plant of supporting the fungus may outweigh the benefits, but in most situations the partnership is mutually advantageous and contributes to plant success. It's a quiet example of cooperation, exchange, support, and steady balance. Mycorrhizae remind us that competition is not the only force shaping ecosystems. Cooperation and mutualism are equally important. The plant and fungus have different strengths and different needs, and by partnering, they can both succeed more fully than either could alone. There's no aggression in this relationship, no domination. It's a trade, a collaboration, an interweaving of lives at the smallest scales that has profound effects on entire landscapes, This partnership has persisted for hundreds of millions of years, shaping the evolution of both plants and fungi and making possible the green, productive ecosystems we see today. With that partnership glowing softly in the background, let's return to the mushroom itself, its parts, shapes, and gentle variety. Mushrooms are incredibly diverse in form, and understanding their structures helps us appreciate both their beauty and their function. Each mushroom's shape reflects its strategy for producing and dispersing spores, and the variety of solutions fungi have evolved is a testament to the creative power of natural selection. Many mushrooms have a cap and a stem, but not all do. The classic mushroom shape, a rounded cap atop a central stem, is familiar and common, but it's just one of many forms. Some mushrooms have no stem at all, growing directly attached to wood or other substrates. Some are shaped like shelves or brackets projecting horizontally from tree trunks. Others are round like puffballs or shaped like coral, antlers, cups, or crusts. The form a mushroom takes is closely related to how it produces and releases spores and to the environment in which it grows. A mushroom growing on the forest floor might benefit from an elevated cap to catch wind currents, while a mushroom growing on the side of a vertical tree trunk might produce spores that fall away from the tree into open air. The diversity of forms is one of the delights of mushroom hunting. You never know quite what shape the next fungus might take. The underside of the cap often has gills, pores, or teeth-like structures, and these features define major groups of mushrooms. Gilled mushrooms, which include many familiar species, have thin, blade-like structures radiating from the stem out to the edge of the cap. These gills are covered with spore-producing cells, and spores form on the surfaces of the gills, eventually dropping into the space between gills and falling, away from the mushroom. Pored mushrooms, including the boletes, have sponge-like undersides covered with tiny holes. Each hole is the opening of a tube, and spores are produced inside these tubes, dropping out through the pores. Toothed fungi have downward-pointing spines or teeth, and spores form on the surfaces of these spines. Each design maximizes surface area in its own way, creating ample room for the production of countless spores. These structures increase surface area for producing spores, which is key to the mushroom's reproductive success. If a mushroom had a flat underside, the area available for spore production would be limited to a circle the size of the cap. But by adding gills, pores, or teeth, the mushroom creates complex three-dimensional surfaces that have far more total area than a flat surface would. Gills, for example, create many vertical surfaces, each one covered with spore-producing cells. The total surface area of all the gills combined can be many times the area of the cap itself. This maximization of surface area allows a single mushroom to produce enormous numbers of spores, sometimes billions from a single fruiting body. This abundance is necessary because spore survival rates are very low, and the mushroom must produce vast quantities to ensure that at least a few spores will successfully germinate and establish new mycelia. Gilled mushrooms release spores from the edges and faces of their gills, a process that's both elegant and efficient. The gills are oriented vertically, which allows spores to drop straight down into the spaces between the gills under the influence of gravity. Specialized cells called basidia, located on the gill surfaces, produce spores at their tips. When mature, the spores are forcibly ejected from the basidia, a process driven by tiny water droplets that propel the spore outward. This ejection is on a microscopic scale. The spore is shot just a fraction of a millimeter, but it's enough to clear the gill surface and enter the space between gills. Once in that space, the spore falls downward, dropping out from under the cap into the open air. If the mushroom is positioned well, air currents can then catch the spore and carry it away. This system works best when the gills are perfectly vertical, which is why you'll often see mushrooms adjusting their growth to keep the cap level, even when growing on sloped ground. Some mushrooms have pores instead of gills, like many boletes, creating a different but equally effective spore release mechanism. Boletes are easily recognized by their spongy undersides, which are actually masses of tiny vertical tubes packed closely together. Each tube is lined with spore-producing cells, and spores drop down through the tubes and out the pores at the bottom. This design is particularly common in mushrooms that form mycorrhizal relationships with trees. The advantage of pores over gills is durability. The spongy mass is less fragile than delicate. Gills may be better suited to certain conditions. Boletes are often quite substantial mushrooms, and the thick, spongy pore layer can produce truly staggering numbers of spores over the course of the mushroom's life. The pores also allow for steady, continuous spore release, as spores drop out as soon as they mature, without needing to be forcibly ejected. Some mushrooms are shaped like shelves and grow on tree trunks, adapting to their vertical environment. These shelf fungi, also called bracket fungi or polypores, are often tough and woody rather than soft and fleshy. They project outward from the sides of trees, and their undersides, facing downward, are covered with pores or gills from which spores drop. Growing on vertical surfaces offers certain advantages. The mushroom doesn't have to compete for space on the crowded forest floor, and it's positioned right next to its food source if the fungus is decomposing the tree's wood. Many shelf fungi are perennial, growing a new layer of tubes or pores each year, building up a thick layered structure over time. Some of these mushrooms can persist for years or even decades, becoming hard and hoof-like, slowly releasing spores season after season as they break down the tree they're growing on. Puffball mushrooms release spores in little clouds when disturbed, a striking and memorable method of dispersal. Puffballs are round or pear-shaped, and as they mature, their interior tissue breaks down into a mass of powdery spores. When the outer skin dries and cracks, or when something, a raindrop, a passing animal, a curious human, taps or steps on the puffball, spores puff out in a visible cloud, like smoke or dust. This cloud can contain millions of spores, carried away on the slightest breeze. The puffball mechanism is particularly effective in dry conditions, when wind is available to disperse spores over long distances. There's something playful about puffballs. Finding a mature one and tapping it to release a cloud of spores is a small joy that many people remember from childhood walks in the woods. Some fungi produce bright colours, while others blend into forest browns and greys, and this variation serves different purposes. Brightly coloured mushrooms, reds, oranges, yellows, purples, can be warnings to potential predators that the mushroom is toxic or unpalatable. The vivid red of Amanita muscaria, for instance, is iconic and serves as a signal. Other bright mushrooms may use colour to attract animals that will help disperse spores, though this is less common than in flowering plants. Many mushrooms, however, are cryptic in coloration: browns, tans, greys, whites, blending into the leaf litter or wood on which they grow. These colours may help the mushroom avoid being eaten, or simply may not confer enough advantage for bright pigmentation to evolve. The colours themselves are produced by various pigments, and can be useful for identifying mushroom species, as certain pigments are characteristic of particular groups. A mushroom's shape often reflects how it spreads spores, tying form to function in beautiful ways. Tall mushrooms with elevated caps catch more wind. Spreading caps create shade beneath, maintaining the humidity needed for delicate gills. Puffballs enclose spores until the right moment, then release them all at once. Shelf fungi use gravity, letting spores drop away from the tree into open space. Stinkhorns produce foul-smelling slime that attracts flies, which then carry spores away on their bodies. Bird's nest fungi form tiny cup-shaped structures with eggs inside, splash cups that fling spore-containing packets when raindrops hit them. Each strategy is an evolutionary solution to the challenge of getting spores from the parent mushroom out into the environment where they might start new colonies. The mushroom's diversity is like a quiet wardrobe of nature. Many styles, one purpose. Whether gilled or pored, bright or drab, elevated or ground-hugging, each mushroom is ultimately doing the same thing, releasing spores. The diversity arises from the many different ways evolution has found to accomplish this goal under varying conditions. In a single forest, you might find dozens or even hundreds of different mushroom species, each with its own shape, colour, habitat preference, and timing. This diversity is not chaotic, but is instead a collection of finely tuned adaptations, each species occupying its own ecological niche, each contributing to the overall function of the ecosystem in its own particular way. Now we'll drift into the gentle life cycle, how spores travel, settle, and begin new hidden networks. The life of a fungus doesn't end when the mushroom withers. It begins again each time a spore successfully germinates. Understanding the fungal life cycle helps us see mushrooms not as isolated individuals, but as parts of ongoing lineages, each generation contributing to the persistence of the species across time and space. Spores are usually microscopic and very lightweight, perfectly designed for long-distance travel. A typical fungal spore might measure just a few micrometers in diameter, far too small to see with the naked eye. At this size, spores are easily lifted and carried by air. They have very little mass, so they can remain suspended in air currents for long periods, potentially travelling miles from the parent mushroom. The lightweight nature of spores is crucial to fungal dispersal. If spores were heavy, they would simply fall to the ground near the parent mushroom, leading to competition and little expansion of the species' range. But because they're so light and so numerous, spores can spread far and wide, colonising new areas and ensuring that the fungal species can survive even if conditions become unsuitable in one location. Wind can carry spores through forests like invisible dust, distributing them broadly across the landscape. On a breezy day in autumn, the air in a forest is full of fungal spores, though we cannot see them. Studies that sample air in different environments consistently find fungal spores present, sometimes in high concentrations. These spores are part of the natural background of particles in the air, along with pollen, bacteria, and mineral dust. Wind dispersal is passive but effective. Spores simply drift wherever the wind takes them, and because they're so small, they can travel long distances before settling. Some spores may travel just a few feet, landing near the parent mushroom. Others may be carried hundreds or thousands of feet, crossing meadows, roads, or rivers to land in entirely new habitats. Some spores travel by water splashes or along damp surfaces, an alternative dispersal strategy suited to certain environments. When raindrops hit a mushroom or the ground near one, they can splash spores into the air, or carry them along the surface of soil or leaves. This splash dispersal is common in mushrooms that grow close to the ground or in wet environments. Some fungi produce sticky spores that adhere to water droplets, ensuring they're carried along when water moves. In very wet habitats, like mossy forests or areas near streams, water dispersal can be as important as wind dispersal. Spores might be washed into streams and carried downstream, or they might be splashed from one leaf to another, gradually moving through the environment in tiny liquid-borne steps. Animals can also help move spores on fur, feet, or by eating mushrooms, creating yet another dispersal pathway. Some mushrooms produce odours that attract insects, slugs, or other small animals. These animals may feed on the mushroom tissue, ingesting spores in the process. The spores can pass through the animal's digestive system and be deposited elsewhere in its feces, potentially in a nutrient-rich package that helps the spore germinate. Other animals simply brush against mushrooms and pick up spores on their fur or feathers, carrying them to new locations. Larger animals like deer, squirrels, and birds can transport spores over considerable distances this way. Some fungi, especially underground truffles, rely almost entirely on animal dispersal. Truffles produce strong scents that attract animals like rodents, pigs, and deer, which dig up and eat the fruiting bodies, dispersing the spores in their droppings. When a spore lands in a suitable place, it can germinate into a new fungal thread, starting the cycle anew. Germination requires the right conditions: sufficient moisture, appropriate temperature, and a substrate that can provide food. If these conditions are met, the spore absorbs water, swells, and begins to grow. A tiny hypha emerges from the spore, extending into the surrounding environment. This first hypha is the beginning of a new mycelium. It grows, branches, and starts to explore its surroundings, seeking nutrients. If conditions remain favourable, the hypha will continue to grow, forming a network that can persist and expand for years or even centuries. This is how fungi colonize new areas, one spore at a time, germinating and establishing new mycelia wherever conditions allow. That thread can grow and branch, forming new mycelium that may one day produce its own mushrooms. The young mycelium starts small, just a few branching threads in the soil or wood. But over time, as it absorbs nutrients and grows, it can become extensive. Months or years after germination, the mycelium may be ready to reproduce. When conditions are right, the right temperature, moisture, and nutrient availability, the mycelium begins to form mushrooms, aggregating hyphae into the structures that will become stems and caps. The mushrooms mature, produce spores, and release them, completing the cycle. The mycelium that produced those mushrooms may continue to live and grow, producing more mushrooms in future seasons, or it may die back if conditions become unfavourable. Either way, the cycle continues, linking generations of fungi through the dispersal and germination of spores. Many fungi require compatible partners to combine genetic material before forming certain mushrooms, adding complexity to reproduction. Fungi have various reproductive strategies, and many species have multiple mating types. For sexual reproduction to occur, two compatible mycelia must meet and fuse. This fusion combines genetic material from both partners, creating genetic diversity in the resulting spores. The fused mycelium can then produce mushrooms that contain this mixed genetic material, and the spores from these mushrooms will carry new combinations of genes. This sexual reproduction is important for generating variation, which allows fungi to adapt to changing conditions and resist diseases. Some fungi can also reproduce asexually, producing spores that are genetically identical to the parent. This can be useful for rapidly colonizing suitable habitats, but it doesn't create the genetic diversity that sexual reproduction does. Fungal reproduction can be complex even when the forest feels simple. From the surface, a forest seems straightforward: trees, shrubs, animals, and the quiet passage of seasons. But beneath this apparent simplicity is tremendous complexity in the reproductive strategies and life cycles of fungi. Some fungi have 2 or more nuclear phases in their life cycles. Some have multiple types of spores, produced in different ways at different times. Some can switch between sexual and asexual reproduction depending on conditions. This complexity is hidden from casual observation, revealed only through careful study. But it's this complexity that allows fungi to be so successful, so adaptable, so resilient across diverse environments and changing conditions. The visible mushroom is often brief, but the mycelium can persist much longer, a reminder of where the real life of the fungus resides. A mushroom might last a few days or a few weeks, but the mycelium that produced it can live for years, decades, or longer. Some individual mycelia are thought to be thousands of years old, persisting underground, slowly expanding, fruiting occasionally when conditions are right. This longevity means that fungi are not just the mushrooms we see. They're the persistent networks that endure through time, connecting past and future through their continuous presence in the ecosystem. When you see a mushroom, you're seeing a brief expression of a much older, much larger life form, a temporary ambassador from the hidden world beneath your feet. In a comforting way, fungi remind us that most important work happens quietly in the background. The mushrooms are beautiful and fascinating, but they're just the tip of the iceberg. The real work, the decomposition, the nutrient absorption, the partnerships with plant roots, the slow spreading through soil, happens out of sight, day after day, year after year. This is true in many areas of life. The visible, dramatic, moments are supported by countless unseen efforts. Fungi teach patience and humility. They show that steady, quiet persistence can accomplish vast things over time, and that you don't need to be loud or showy to be essential. With those tiny spore journeys in mind, let's explore how fungi fit into whole ecosystems, supporting soil, plants, and small creatures. Fungi are not isolated organisms. They're deeply embedded in the ecosystems where they live. Their activities influence soil structure, plant health, animal populations, and the cycling of nutrients. Understanding these ecosystem roles helps us appreciate fungi not just as interesting organisms, but as critical players in the natural world. Fungi help build healthy soil by breaking down organic matter into usable nutrients, a foundational ecosystem service. Soil is not just ground-up rock. It's a complex mixture of minerals, organic matter, water, air, and living organisms. The organic component of soil, the dark, crumbly humus, is largely the product of decomposition. As fungi and bacteria break down leaves, wood, and other plant material, they create humus, a stable form of organic matter that improves soil structure, holds nutrients, and supports plant growth. Humus gives soil its fertility, its ability to retain moisture, and its characteristic dark color. Without the decomposing action of fungi, soils would be far less productive. The nutrients locked in dead plant material would remain unavailable to living plants, and the soil would lack the organic matter that gives it structure and fertility. This process contributes to the rich smell of forest soil after rain, a scent that many people find pleasant and evocative. That earthy smell is partly due to compounds released by soil microbes, including fungi. One compound often associated with this scent is geosmin, produced by certain bacteria, but fungi contribute their own volatile compounds to the complex bouquet of forest soil. The smell is a signal that the soil is alive and active, full of organisms working to break down organic matter and cycle nutrients. It's the smell of decomposition, not as something unpleasant, but as something vital and generative. Breathing in that scent after a rain, you're experiencing the chemical signature of the ecosystem's recycling process. Fungi can help soil hold moisture by improving structure over time, particularly through the production of hyphae and sticky compounds. Fungal hyphae bind soil particles together, creating small aggregates that give soil structure. These aggregates create pore spaces in the soil, tiny gaps where air and water can move. Good soil structure means that water can infiltrate rather than running off, and that the soil can hold moisture in its pores, making it available to plant roots over time. Some fungi produce glomalin, a sticky protein that further stabilizes soil aggregates. Over time, the activity of fungi and other soil organisms creates a soil with good tilth, easy to work, able to absorb and hold water, and resistant to erosion. This improved soil structure is one of the less visible but highly important contributions fungi make to ecosystem health. Many insects and small animals feed on fungi or live near fungal growth, creating food webs centered on fungal resources. Fungal fruiting bodies, mushrooms, are food for a wide range of organisms. Slugs and snails graze on mushroom tissue. Insects lay eggs in mushrooms, and their larvae feed and develop inside the fruiting bodies. Some beetles specialize in feeding on particular types of fungi. Springtails and mites feed on fungal hyphae in the soil. Even vertebrates like squirrels, deer, and small rodents eat mushrooms, sometimes selectively seeking out certain species. This means that fungi support animal populations not just by recycling nutrients, but by serving directly as food. In some ecosystems, the seasonal appearance of mushrooms is an important food source for wildlife, providing protein and nutrients at critical times. Some animals rely on fungi as part of their diet, either occasionally or as a primary food source. Northern flying squirrels, for example, feed heavily on truffles and other underground fungi, and they play a role in dispersing the spores of these fungi through their feces. Some insects have obligate relationships with fungi. They cannot complete their life cycles without fungal food sources. Certain beetles vector fungal spores to new logs, where the fungi decompose the wood and provide food for beetle larvae. In tropical regions, leafcutter ants cultivate fungi in their nests, feeding the fungi with fresh-cut leaves and then eating the fungal tissue. These intricate relationships show how deeply fungi are woven into the fabric of ecosystems, not just as background organisms, but as central players in food webs and ecological interactions. Fungi can also influence which plants thrive in a given area through their partnerships, shaping plant community composition. If a particular plant requires a particular mycorrhizal fungus to grow well, the distribution of that fungus can determine where the plant can successfully establish. Conversely, if a plant can form partnerships with many different fungi, it may be more flexible and able to grow in a wider range of conditions. Some invasive plants succeed partly because they can form partnerships with local mycorrhizal fungi, gaining the benefits of these relationships as soon as they arrive in a new area. On the other hand, some rare or endangered plants may struggle in part because their specialized mycorrhizal partners are also rare or have declined. Understanding these fungal-plant relationships is increasingly recognized as important for conservation and restoration, as reintroducing the right fungi can sometimes help re-establish native plant communities. Forest ecosystems depend on these underground relationships for stability, with mycorrhizal networks linking trees and sharing resources. Recent research has revealed that mycorrhizal networks can connect multiple plants, even plants of different species, creating what some have called a wood wide web. Through these networks, nutrients and even chemical signals can move between plants. A large, well-established tree might share sugars with smaller shaded seedlings through fungal connections, potentially helping the next generation survive in low light. If a tree is attacked by insects, it might send chemical signals through the mycorrhizal network that prompt neighbouring trees to increase their own defences. These findings suggest that forests are more interconnected than previously thought, with fungi playing a central role in linking individual plants into a cooperative community. When conditions change, fungal communities can shift too, responding to alterations in climate, moisture, or plant composition. If a forest experiences a drought, drought-tolerant fungi may become more common while moisture-loving species decline. If tree composition changes, for example, if a forest transitions from oaks to pines, the mycorrhizal fungi associated with those trees will shift accordingly. If temperatures rise or rainfall patterns change, fungal species that thrive in the new conditions may replace species that thrived in the old conditions. These shifts can happen gradually, over years or decades, and they can have cascading effects on the plants and animals that depend on fungal. Understanding how fungal communities respond to environmental change is an active area of research, with implications for predicting how ecosystems will respond to climate change and other disturbances. Even so, fungal roles, recycling and partnering, remain steady themes in nature, constants amid the changes. No matter what species of fungi are present, the basic functions remain the same. Dead material gets decomposed and recycled. Living plants form partnerships with fungi to improve nutrient uptake. These processes have been happening for hundreds of millions of years and will continue as long as there are plants and fungi. The specific players may change, but the play remains the same. This constancy is reassuring. It speaks to the resilience of ecosystems and to the fundamental importance of fungi in the natural world. A forest can be seen as a community above ground, supported by a quieter community below. The trees, shrubs, wildflowers, birds and mammals are the visible members of the forest community, the ones we notice and appreciate. But beneath them is another community, the soil organisms, the decomposers, the mycorrhizal networks, that makes the above-ground community possible. This below-ground community is just as diverse and just as important, even though it's mostly invisible. The two communities are connected, each depending on the other, each shaping the other. Fungi are key members of the below-ground community, and understanding their roles helps us see forests as integrated wholes rather than just collections of trees and animals. Now we'll gently touch on humans and mushrooms, not as rules or warnings, but as calm notes about curiosity and study. Humans have long been fascinated by mushrooms, and our relationship with fungi is complex, encompassing food, medicine, culture, and science. Approaching this relationship with curiosity and respect can deepen our appreciation for fungi and their place in the world. People have studied mushrooms for centuries in many cultures, recognizing both their practical uses and their intrinsic interest. In ancient times, people learned which mushrooms were safe to eat and which were poisonous, knowledge passed down through generations. Some cultures developed sophisticated mushroom cultivation techniques, growing fungi for food long before modern agriculture existed. In Europe, truffle hunting became an art, with trained animals helping people locate the prized underground. Fungi. In Asia, certain mushrooms were valued not just as food, but as medicine, used to treat various ailments. Indigenous peoples around the world have incorporated mushrooms into their diets, ceremonies, and healing practices, developing deep knowledge of local fungal diversity. The scientific study of fungi is called mycology, a field that encompasses everything from the molecular biology of fungal cells to the ecology of fungal communities. Mycologists identify and classify fungi, study their life cycles, investigate their biochemistry, and explore their roles in ecosystems. The field has grown enormously in recent decades as new molecular techniques have allowed scientists to detect and identify fungi that don't produce visible fruiting bodies or that are otherwise difficult to study. DNA sequencing has revealed that fungal diversity is far greater than previously thought, with thousands of species still unnamed and unstudied. Mycology is a vibrant field full of discoveries and unanswered questions, appealing to scientists interested in everything from ecology to genetics to biochemistry. Scientists classify fungi by genetics, structure, and life cycles, creating a taxonomy that helps organize the immense diversity of fungal life. Early classifications were based on visible characteristics: the shape of the mushroom, the color of the spores, the structure of the gills or pores. As microscopy improved, scientists began to examine spore shapes, hyphal structures, and other fine details. More recently, genetic analysis has revolutionized fungal taxonomy. By comparing DNA sequences, scientists can determine evolutionary relationships between fungi, grouping species that are closely related and separating those that only look similar but are not closely related. This genetic approach has led to many reclassifications and has clarified the fungal tree of life, showing how different groups of fungi are related and how they have evolved over time. Some mushrooms are used as food, while others are not eaten, and distinguishing between them requires knowledge and caution. Edible mushrooms have been part of human diets for millennia. Mushrooms like button mushrooms, shiitakes, oyster mushrooms and portobellos are cultivated commercially and widely available. Wild mushrooms like chanterelles, morels and porcini are prized by foragers and chefs for their flavours and textures. But many wild mushrooms are inedible, and some are dangerously toxic. Eating the wrong mushroom can cause illness or even death, so proper identification is critical. People who forage for wild mushrooms often spend years learning to identify species reliably, using field guides, attending workshops, and seeking guidance from experienced foragers. The rule, when in doubt, throw it out, is wise. No mushroom meal is worth the risk of poisoning. Fungi are also used in making bread rise, brewing and fermenting foods, though those are yeasts rather than typical mushrooms. Yeasts are single-celled fungi, lacking the complex multicellular structures of mushrooms, but they're fungi nonetheless, and they're enormously important to human culture and cuisine. Yeasts ferment sugars into alcohol and carbon dioxide, processes harnessed for making beer, wine, and bread. Baker's yeast makes dough rise, creating the light texture of bread. Brewer's yeast ferments the sugars in grain or fruit, producing alcohol and the flavours of beer and wine. Other fungi are used in fermenting foods like soy sauce, miso, tempeh, and certain cheeses. The blue veins in blue cheese, for instance, are colonies of Penicillium mold. These culinary fungi are so integrated into human foodways that it's hard to imagine cuisine without them. Some fungi produce compounds used in medicine and research, contributing to human health and scientific knowledge. The most famous example is penicillin, the antibiotic derived from Penicillium mold, which revolutionized medicine and saved countless lives. Other fungi produce antibiotics, immunosuppressants, cholesterol-lowering drugs, and other medically important compounds. Some mushrooms produce compounds being studied for potential anti-cancer, anti-inflammatory, or immune-modulating effects. Fungi are also important model organisms in biological research. Yeast cells, for example, are used extensively in genetic and molecular biology studies because they're simple, easy to grow, and share many fundamental cellular processes with human cells. Insights gained from studying fungi have broad applications in medicine, agriculture, and biotechnology. Fungal enzymes are studied for their ability to break down tough materials, with potential applications in industry and environmental cleanup. The same enzymes that allow fungi to decompose wood and other plant materials can be harnessed for human purposes. Cellulose and ligninase enzymes, for instance, are being explored for breaking down agricultural waste, producing biofuels, and improving paper manufacturing. Some fungi can break down pollutants like petroleum hydrocarbons, pesticides, and even plastics, leading to interest in using fungi for bioremediation, cleaning up contaminated sites naturally. Research into fungal enzymes is ongoing, with scientists seeking to understand how these enzymes work and how they might be used to solve practical problems. Mushrooms can be grown in controlled environments for study and cultivation, making fungi accessible for research and food production. Cultivating mushrooms allows scientists to study fungal biology in detail, controlling variables and observing growth and reproduction under different conditions. It also provides a sustainable source of food. Mushroom cultivation can be done on a small scale, in a home garden or even indoors, or on a large industrial scale. Some mushrooms are easier to cultivate than others. Button mushrooms and oyster mushrooms grow readily on composted materials or straw. Shiitakes grow on logs or sawdust blocks. Other mushrooms, particularly mycorrhizal species, are more difficult or impossible to cultivate because they require living plant partners. But for those that can be grown, cultivation offers a way to enjoy mushrooms without relying on wild foraging, and a way to study fungi year-round. Learning about fungi often reveals how connected ecosystems truly are, opening our eyes to relationships we might not have noticed. When you start to understand that most plants have fungal partners, that dead wood is habitat and food for countless organisms, that mushrooms are just visible moments in long underground lives, the forest becomes a different place. You see connections instead of isolated organisms. You notice the cycling of nutrients, the flow of energy, the partnerships and dependencies that link life forms together. This ecological perspective is one of the great gifts of studying fungi. They're such integral parts of ecosystems that learning about them means learning about the systems themselves. Fungi invite a slow kind of curiosity. Notice, observe, and appreciate the quiet work, There's no need to rush when learning about fungi. They're patient organisms, and they reward patient observation. You might visit the same fallen log week after week, watching as different mushrooms appear and fade as the wood gradually softens and crumbles. You might photograph mushrooms, noting their shapes and colours, trying to identify them later. You might simply sit quietly in the forest and think about the hidden networks beneath your feet, the silent decomposition, the slow exchanges between roots and hyphae. This kind of engagement is meditative, calming, and enriching. It asks nothing but your attention and offers in return a deeper connection to the natural world. To finish, we'll bring the forest's recycling team back to bedtime scale. Soft transformations, slow cycles, and a calm mind. Fungi teach lessons that extend beyond ecology into how we might think about our own lives. Lessons about patience, about the value of quiet work, about cycles of growth and decay, about cooperation and connection. Decomposition is not a harsh ending. It's a quiet return of materials to the soil, a transformation rather than a termination. When a leaf falls or a tree dies, it doesn't simply vanish. It becomes something else: food for fungi, habitat for insects, nutrients for future plants. This transformation is gradual and gentle, a slow yielding to the processes of decay. There's no violence in it, just chemistry and biology working at their own pace. Thinking about decomposition in this way can be comforting. Endings are not really endings, they're transitions, returns, contributions to the continuation of life. Fungi help transform fallen trees into nutrient-rich ground for new growth, completing the cycle that allows forests to renew themselves. A tree that lived for 100 years, accumulating carbon and nutrients, eventually falls. Over the next few decades, fungi and other decomposers will dismantle that tree, releasing its stored resources back into the ecosystem. Where the tree once stood, new seedlings may grow, nourished by the soil enriched with nutrients from the fallen giant. This is succession at work, the process by which ecosystems change and renew themselves over time. Fungi are central to this process, the agents of transformation that allow old structures to become new possibilities. This cycle supports future plants without needing loud change, operating on nature's own timeline. There are no announcements, no sudden shifts. The cycle simply continues day by day, year by year. Seeds germinate, plants grow, plants die, fungi decompose, nutrients return to soil, new seeds germinate. The cycle is ancient and reliable, requiring no intervention, no management, no haste. It's a system that works because each part does its job in its own time. This patience is built into nature, and observing it can help us find patience in our own lives. Many forest nutrients are reused again and again through these processes, creating a kind of natural economy. In ecosystems, waste is rare because everything is eventually recycled. The carbon that was once in a tree might become part of a mushroom, then return to the air as CO2, then be taken up by a new tree through photosynthesis. The nitrogen that was in a fallen leaf might be absorbed by a fungus, passed to a plant through a mycorrhizal connection, incorporated into new leaves, and eventually return to the soil again when those leaves fall. This reuse is efficient and sustainable, a model of circularity that human systems often aspire to but rarely achieve. Mycelium can link different parts of the forest through shared soil spaces, creating physical connections that integrate the ecosystem. The hyphal networks spread through soil, touching roots, decomposing organic matter, exploring pore spaces. These networks can be extensive, connecting trees, shrubs, and herbaceous plants in an underground web. Through these connections, the forest becomes more than a collection of individual plants. It becomes a community, interlinked and interdependent. This connectedness is invisible from the surface, but it shapes how the forest functions, how nutrients move, how plants support each other. Mushrooms appear and fade, but the fungal network can remain, a reminder that persistence doesn't require constant visibility. We often equate presence with visibility, but fungi teach us that the most enduring aspects of an organism can be hidden. The mushroom is temporary, but the mycelium endures. We might draw parallels to our own lives. The visible accomplishments, the public moments, are supported by the quieter, ongoing work we do day after day. Resilience and persistence often happen beneath the surface, in the steady, unglamorous work that sustains us over time. Rain often encourages mushroom growth because fungi thrive In moisture, responding to environmental cues with precise timing. A dry spell might mean no mushrooms for weeks, but a good rain can trigger a flush of fruiting within days. This responsiveness shows how attuned fungi are to their environment, how they wait for the right conditions rather than forcing growth when times are unfavourable. There's wisdom in this, knowing when to act and when to wait, responding to conditions rather than ignoring them. The smell of damp forest earth can be linked to microbial life and decomposing matter, a sensory reminder of the hidden activity. That rich, earthy scent is the smell of life in transformation, of organisms breaking down and building up, of the forest's respiratory and digestive systems at work. It's a smell that many people find comforting, perhaps because it's associated with forests, with nature, with places that feel alive and whole. Breathing in that scent, we're taking in molecules released by fungi and bacteria, tangible evidence of the invisible work happening all around us. Fungi show that slow change can be healthy and natural, offering an alternative to the speed and urgency that often dominate modern life. We live in a culture that values speed, that wants results now, that can become impatient with processes that take time. Fungi remind us that many of the most important processes cannot be hurried. Decomposition takes the time it takes. Mycelium grows at its own pace. Mushrooms appear when conditions are right, not when we demand them. This natural slowness is not laziness or inefficiency. It's the appropriate pace for the work being done. Accepting this can reduce anxiety and help us align ourselves with natural rhythms rather than fighting against them. In a cozy way, fungi teach that letting go can be part of making space for new calm. Just as a fallen tree must decompose to make room and resources for new growth, we sometimes need to let go of things, old habits, outdated beliefs, finished projects, to make space for new possibilities. Holding on tightly to everything, refusing to let anything end or change, creates stagnation. Letting go, allowing natural conclusions, accepting endings as part of a cycle rather than as failures, these can bring a sense of calm and renewal. Fungi, in their patient work of breaking down and transforming, model this graceful approach to endings. Now we'll settle everything gently, like a forest floor at dusk, quiet, soft, and ready for rest. As the day fades in a forest, light dims, temperatures cool, and the forest settles into evening. The birds grow quiet, the breeze calms, the forest floor, covered in leaves and moss, becomes a soft bed where small creatures nestle and where fungi continue their invisible work. There's a peacefulness to this transition, a sense of the day releasing its grip and night arriving gently. We can invite that same gentle settling into our own experience, letting thoughts quiet, tensions ease and rest, approach softly. Mushrooms are brief appearances of a much larger hidden life below, ephemeral expressions of persistent organisms. When you remember this, mushrooms take on new meaning. They're not isolated objects, but connected to vast networks, brief moments of visibility and long lives lived mostly underground. This perspective can shift how we see many things, recognizing that what's visible is just a small part of a larger whole, that there's always more happening beneath the surface. Mycelium works quietly, absorbing, sharing, and recycling day after day without fanfare. It doesn't seek attention or recognition. It simply does its work, responding to conditions, growing where growth is possible, forming partnerships, breaking down materials. This quiet competence is admirable. There's no drama, no crisis, just steady function. In our own lives, much of what sustains us happens just as quietly. The routines we maintain, the small kindnesses we offer, the daily work we do. This quiet work is valuable, even essential, though it may never be celebrated. Forests stay healthy partly because fungi keep nutrients moving, preventing depletion and maintaining productivity. The cycling of nutrients is fundamental to ecosystem health, and fungi are key drivers of this cycling. By breaking down dead material and releasing nutrients, by transferring nutrients between plants through mycorrhizal networks, fungi ensure that resources remain available and that ecosystems don't run down over time. This maintenance work, invisible but crucial, is what allows forests to persist for centuries and millennia. The mushroom's cap and gills are simple tools for spore release, evolved solutions to the challenge of reproduction. There's elegance in this simplicity, no unnecessary complexity, just the structures needed to do the job. The cap protects the gills, The gills maximize surface area, the spores drop and drift away. It works, and it has worked for millions of years. Sometimes, simple solutions are the best ones, refined through time until they're perfectly suited to their purpose. Spores travel lightly, trusting wind and water to carry them, surrendering to forces beyond their control. A spore has no agency, no ability to steer or choose its destination. It simply releases and drifts, trusting in numbers and chance. Most will fail, but some will find the right spot, germinate, and continue the cycle. There's a kind of faith in this process, a trust in the mechanisms of dispersal that have worked for countless generations. We too must sometimes trust processes we cannot control, releasing our grip and allowing outcomes to unfold. Mycorrhizal partnerships show that cooperation can be as important as competition, balancing the narratives we often hear about nature. While competition and survival of the fittest are real and important, cooperation and mutualism are equally prevalent and equally significant. Fungi and plants cooperate, sharing resources, supporting each other, creating outcomes that benefit both partners. This cooperation is not altruistic in the human sense. It's driven by mutual benefit, but it's cooperation nonetheless, and it shows that success in nature often comes not from outcompeting others but from finding ways to work together. The forest's calm stability comes from many small processes happening slowly, an emergent property of countless interactions. No single organism or process makes the forest stable. Instead, stability emerges from the integration of many parts. Decomposition here, growth there, partnerships everywhere, nutrients cycling, water percolating, energy flowing. Each small process contributes to the whole, and the whole is far more stable and resilient than any single part. This is how complex systems work, and it's a comforting reminder that stability doesn't require perfection or control. It arises naturally from healthy interconnection. Thinking about mushrooms can soften the mind, like watching mist settle on leaves, gently redirecting attention to quiet, natural processes. There's something inherently calming about mushrooms and fungi. They're not threatening or aggressive. They don't demand anything. They simply are, quiet, patient, doing their work in their own time. Contemplating them, imagining mycelium spreading through soil, picturing spores drifting on wind, visualizing the slow transformation of a fallen log. These thoughts can quiet mental chatter and invite a meditative state, a soft focus that allows the mind to rest. Tonight, you can let your thoughts decompose gently, breaking into smaller, quieter pieces, just as fungi break down complex molecules into simpler ones. Thoughts that are tangled or troubling can be allowed to fragment, to lose their sharp edges, to soften and dissolve. There's no need to hold on to thoughts tightly. They can drift apart, their components released, their energy dispersed. In the same way that fungi transform a fallen tree into soil, you can allow your thoughts to transform into something quieter, something more restful, something that nourishes rest rather than preventing it. And you can rest, knowing the world knows how to renew itself, softly and patiently, in cycles that have continued for eons and will continue long after tonight. The forest doesn't need your vigilance to keep functioning. The fungi will continue their work. The mycelium will grow. The cycles will turn. You are part of these cycles, connected to them through breath and food and the shared chemistry of life, but you don't have to manage them or control them. They go on, reliably, and you can trust in that continuation. You can release the day, release your concerns, and allow yourself to settle into sleep, knowing that the world is taking care of itself, that you're held by systems far older and wiser than worry, that rest is natural and necessary and safe. Take a slow inhale and then a longer exhale and imagine your mind like a quiet forest floor, soft, warm and gently settling into sleep. The forest floor is forgiving, supporting whatever rests upon it without judgment. It's made of countless small pieces, leaf fragments, crumbled wood, fungal threads, all loosely connected, all part of a whole. Your mind can be like this, soft and accepting, each thought just a small fragment settling into place, no thought too heavy or too sharp, everything gradually coming to rest. The warmth of the forest floor, accumulated from the day's sun and held in the organic matter, is the warmth of being alive, of being held, of being part of something larger. And as you settle, as your breathing slows and deepens, as your body relaxes into the support beneath you, you can imagine yourself becoming part of that quiet forest floor, sinking into rest as naturally as a leaf falling, as gently as a spore landing, as peacefully as the forest itself settling into the stillness of night. The next story is about to begin. Please relax and enjoy.